What? Not responding. Wait. What would be the problem? Network, eh?
Yeah.
Good evening. Good evening. Good evening. Good evening. My network is not stable. I don't know what is the problem is. What the problem is, my network is not stable. Let's increase the volume. Good evening, guys. My network is not that stable. I'm not sure what the problem is. But we're just going to continue now. We are going to start. We are going to start now. We're going to start now. All right, like I promised, guys, today we are going through paper 1. We are going through paper 1 for 2021 as per your request. This is what we are going to do. We are going to go through geography paper 1 in November 2021. So I really need your participation as well, as we will be going through this paper. I'll also give explanations as well to some of the concepts so that you understand what is it that we are supposed to do in different set of questions. Okay, so this is the paper. It's the 2021. This is the paper. It's the 2021 November NSC. Let's just start right away because we have got 2 sets of papers to go through. That is the 2024 Gauteng, this paper, and this paper. Let's start now with the 2021. So you have got now in your section A, you have got question 1, which covers climate and weather. So let's go through the questions now. Just give me a thumbs up if you can see the questions clearly. Give me a thumbs up. Give me a thumbs up so if you can see the questions clearly. Give me a thumbs up if you can see the questions clearly. Okay, sharp. Let's go through now. Climate and weather. Various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question numbers 1.1.1 to 1.1.8. So I will also be explaining. If it happens that we come across something that you do not understand, please, I'm looking at your comments. You can ask, say, can you just give a bit a deep explanation in as far as whatever concept is concerned. Okay, so the first one is mid-latitude occurs between. So on the first one, the concept that is being assessed there is the mid-latitude. Of course, we will try by all means to add as much information as possible. Occurs between. So this question, before we get the answer, I know most of you know the answer. Okay, so we are saying now, I'll take you back to the global air circulation. What do we have? We have got something like this, né? Okay, then what we have at the center, we have got the equator, which is at 0 degrees. We have got the equator at 0 degrees. Then from the equator at 30 degrees north and south, 30 degrees north, 30 degrees south. What do we have? We have got the subtropical high, you know. Then here what do we have? We have got the subpolar low at 60 degrees north and 60 degrees south. Then here we have got the polar high. There we have got the polar high as well. So the question now is asking, the mid-latitude occurs between dash north and south of the equator. So our mid-latitude is in the middle of the latitude, that is between 30 to 60. 30 to 60. This is where we have got our mid-latitude in the 30 to 60, which means from the options that is given, what is the answer? That is, your answer is B. So you find it in this between 30 to 60 north and south of the equator. That's where you have got your mid-latitude. So I've just drawn this diagram which shows the global air circulation, the pressure belts. So you've got the equatorial low, subtropical high, subpolar low, polar high, both north and south of the equator. So our mid-latitude is found occurs between 30 degrees to 60 degrees north and south of the equator. So your answer there is B. Okay, mid-latitude is steered or driven by. What drives the mid-latitude? Okay, in order for you to be able to answer these questions again, let me go back to the same diagram of the global air circulation. What do we have here? Remember, from 0 to 30, we have got the tropical easterlies. Here we have got the tropical easterlies, né? Tropical easterlies. Okay. Tropical easterlies, I'll just say TE. Then between 30 and 60, we have got the westerlies. Okay, we have got the westerlies. We also have the westerlies here. Then here we have got the polar easterlies. We have got the polar easterlies. So this is how it's like. So we have said that it occurs between 30 and 60. If you look at our 30 and 60, what drives the mid-latitude is these westerlies. Westerlies is what drives that is what drives the mid-latitude cyclone. It is steered by the westerlies. This is where our mid-latitude occurs. So it's within the 30 degrees north and south of the equator, of course. So it is steered or driven by these westerlies. It means now for 1.1.2, what is the answer? 1.1.2, our answer, what is our answer for 1.1.2? I've explained. I want you to give me the answer from the options that are given. What is the answer there for 1.1.2? I've explained. What is the answer? That is D. It is steered by the westerlies. So that is your answer there. That is your answer there. It is steered by the westerlies. Because here, when you look at your this diagram that I'm using, you have got your equatorial low, subtropical high, subpolar low, between 30 and 60. That's where we have got the westerlies north and south of the equator. So it is steered by the westerlies. Let's move on now to 1.1.3. 1.1.3, it reads the change in wind direction. Change in wind direction. Okay. In the mid-latitude cyclone, okay, in the southern hemisphere. What you need to understand now is a low pressure system, let's say just a cyclone in the southern hemisphere, it moves in a clockwise direction, and in the northern hemisphere it moves in an anti-clockwise direction. So the wind direction that we are talking about, the change, is what we refer in the southern hemisphere as backing. We call that backing. That is the change, because it's supposed to move in a clockwise, but when it changes to anti-clockwise, that's what we refer to as backing. In the northern hemisphere, of course, when it changes now to clockwise, we call it veering. We call it veering. That is the difference between the two. So our answer here on 1.1.3, 1.1.3 is backing. Remember, in the southern hemisphere, it moves in a clockwise direction. So when it changes to anti-clockwise, that's what we refer to as backing in the southern hemisphere. In the northern hemisphere, obviously, it moves in a what? In a clockwise, in an anti-clockwise direction. When it changes to clockwise, that is veering. That is the difference. So it's the change in wind direction. In the southern hemisphere, remember our cyclone, our low pressure system, it moves in a clockwise. So if it changes direction, that is backing. In the northern hemisphere, it moves in an anti-clockwise. If it changes direction to clockwise, that's what we refer to as veering. So in the southern hemisphere, we call it backing. That is our answer. Do we all understand, so that I can proceed to the next one? Do we all understand, so that I can proceed to the next one? That is the difference now between your backing and veering. Both of them explains the change in wind direction. Okay. Okay. Let's move on to now 1.1.4. I'm seeing someone saying no. We are saying now the cyclone in the southern hemisphere, it moves in a what? In a clockwise direction. So when there is a change in wind direction, we call that backing. That is in the southern hemisphere. If in the northern hemisphere, it moves in an anti-clockwise. So when it changes to clockwise, we call that veering. That's what we call veering. So our answer for 1.1.3, we have said it's backing, because it said the change in wind direction of the mid-latitude cyclone in the southern hemisphere. It is called backing. Remember, it moves in a clockwise. So if there is a change in wind direction, it's going to be anti-clockwise. That's what we refer to as backing in the southern hemisphere. Can I proceed to the next? Can I proceed? Can I proceed? Can I see if you understand? Then I can proceed to the next one. So backing, we are saying anti-clockwise in the southern hemisphere. Veering, we are saying what? Veering, we are saying what? Clockwise in the northern hemisphere. That's basically what we are saying. Okay, let's move on to 1.1.4. The front below, what is the answer there? Remember, when we talk about the fronts, we have got, of course, something that looks like this. Okay, then we have got something that looks like this. Can you identify these two types of fronts? Can you identify these two types of fronts? Of course, it's a warm. It has got a semicircle. That is your warm front. Yeah, that is your warm front. That is your warm front there. The answer is C. Let's move on to the next one. 1.1.5. 1.1.5. Okay. What do we have? The mid-latitude below is in the... Which stage is this mid-latitude in 1.1.5? What is the stage? What is the stage? What is the answer? Remember, which stages do we have? Which stages do we have? Okay, the initial, we have got the wave development. That one is a mature. Why are we saying it's a mature stage? Because there's a well-developed cold front and well-developed warm front. We also have a well-developed warm sector there. That's why we say it is a mature stage, because it is at the mature stage where we have got a fully developed cold front and a fully developed warm front. We also have this, both the sectors are not fully developed. That is the warm sector, the cold and the cool sector. All of them are evident. That's why we are calling this a mature stage. So that is the mature stage. That is the mature stage. The initial, what it does is just what you see when you have got the warm and moist from the subtropical and the cold from the polar, separated by a polar front. That will be your initial. The wave development, obviously, as they start to be some disturbances in terms of upper air movements, obviously the wave starts to develop. That is your second stage. So this is the mature stage. Let's move on to the next one, 1.1.6. The conditions experienced behind a cold front. What do we have behind a cold front? Before we move on to look at the question, what do we have behind a cold front? Behind the cold front, there's cold air. Ahead of the cold front, there's warm air, which is the warm sector. Then ahead of the warm front, we have got cool air. If you can be able to identify, here there is cold, here there is warm, here is cool. So that's what we have. So we have got something like this. So the question says the conditions experienced behind the cold front are what is experienced behind the cold front there. Cold front, there's an approaching cold front. Obviously, we are likely to have a drop in temperature, isn't it? The temperature is likely to decrease. Let's look at the options that we have. We are also likely to have an increase in pressure as well. Remember, our high pressure is associated with cold air. Okay, increase in pressure and decrease in temperature, which means what is the answer there for 1.1.6? What is the answer? Sorry, what is the answer? What is the answer for 1.1.6? Increase in pressure is okay. Temperature drops as well. So there's likely to be an increase in pressure and a decrease in temperature. So what would be the answer from the options that are given them? What would be the answer 1.1.6? That is A. That's correct. A. That's correct, guys. That is correct. That is correct. That is A. Increase in pressure and also decrease in temperature. We are saying it's not B. It's increase in pressure and decrease in temperature. What we are saying, I want you to look at this diagram. Can you see here? We have got a cold front. Behind the cold front, there is cold air. Cold air, remember, it's what? It's heavy, it's denser. What does it do? It subsides, it sinks. Cold air is associated with high pressure. Warm air is associated with low pressure. So we cannot say low pressure and decrease in temperature. The answer there is increase in pressure and decrease in temperature. So it means our answer here is A. Our answer is A. That is our answer. Do you all understand 1.1.6 so that we can move on to 1.1.7? If you understand 1.1.6, you give me a thumbs up, then we can proceed. If you understand 1.1.6, do you all agree? Yebo, yes. Let's move on to 1.1.7. So 1.1.7 is saying which symbol illustrates the merging. Okay, which symbol illustrates the merging? Merging, simply, we are simply talking about the occlusion. Okay, when the cold front and the warm front, okay, when they merge, okay, which symbol illustrates that 1.1.8, 1.1.7, sorry, what would be the answer there? I'm seeing a lot of options there. Remember, I think I demonstrated, we have got our, okay, what is the answer there? What is the answer from the options that are given? This is out. This is out. As well, this is out. I want you to check the position where our triangle is, which means the only option that is applicable there is D. Check from here. I'll show you here. Okay. If they are going to merge, I want you to look at this diagram. It means we are going to have our cold front, warm front. Cold front, you see, when they occlude, this is what is going to happen. This triangle is not going to be on the other side. It's going to be on the same side, but we'll have the triangle, then we have got the semicircle. So when they merge, that's what is going to happen. That's what is going to happen. It's going to be like this, which means our answer there is D. D is our answer. Our answer there is D. That's what is going to happen when they occlude. We have got it as D, not this. Okay. The answer there is D. Anyone confused with 1.1.7 before we proceed? The answer there is D, not C. The answer is D. The answer there is D. The answer is D. Okay, you can't see. Let me see if I can be able to. All right. I want you to look at this diagram. There is your, when they merge. When they are going to merge, your triangle will be there, then you have got the semicircle. So you are going to have something like this on D. I want you to refer back to your notes as well, even after this, just to confirm. Your answer there is D. It's not this. It's D. It's not this. Look at this diagram that shows the mature stage. The triangle is not supposed to face this other direction, to be on the same direction, but it's showing now we have got there. Okay, check here what we have here. So the answer there is D. This is what shows the occlusion. They have merged, they have joined. So the answer there is D. The answer is D, it's not C. It's D, it's D. Are we fine so that we can move on to the next one? Are we fine so that we can move on to the next one? This is more stationary, but this is the correct one. Okay, let's move on to 1.1.8. The station model generally associated with the cold front in the southern hemisphere. The station model associated with the cold front in the southern hemisphere. Take note, station model of the cold front in which hemisphere? Southern hemisphere. So which means it's supposed to be to move in a clockwise. It's supposed to move in a clockwise. It's supposed to move in a clockwise. Which one is it there? Cold front. You remember a cold front is supposed to be associated with what? overcast, of course, unstable weather condition. So from the option that is given, which one is our answer? Which one is the correct answer? Which one is the correct answer? Which one is the correct answer? Remember, we name the wind from where it's coming from. From where it's coming from. I want you to consider this one is out. This one is out. Okay. Those ones who are saying D, why are you saying D? Is it moving in a clockwise or anti-clockwise direction? Check between the two. Which one is moving in a clockwise direction? Which one is moving in a clockwise direction? The answer there is A. That's correct. I'm seeing some of you writing A. The answer there is A. Because remember, it's coming from the northwest, which means it moves like this. That makes it clockwise in the southern hemisphere. Are you following? The answer there is A. Because it's coming from here. We name the wind from where it's coming from. It's coming from the northwest, which means it's gonna move like this, which is clockwise. That is in the southern hemisphere. Remember, our cyclone in the southern hemisphere, it moves in a clockwise, not anti-clockwise. Okay, so the answer there is A. The answer is A. Can we move on to the next one? Can we move on to the next one? Someone is saying it's D. Why are you saying it's D? The answer is A. Remember, we name the wind from where it's coming from. It's coming from here, then it moves like the system is moving in a clockwise direction. So the answer there is A. It's moving in a clockwise direction. The answer there is A. It's moving in a clockwise direction. This one is southeasterly. You can say it's coming from the southeast. You can say it's coming from the southeast. So it goes the other way around, which is anti-clockwise. Which is anti-clockwise. So the answer there is here. It's in the southern hemisphere. It's a cyclone, low pressure in the southern hemisphere. It moves in a clockwise. This one will move in an anti-clockwise. That's why we are saying D is wrong. The answer is A. The answer is A. Can I move on to the next one? If you understand, give me a thumbs up. This one will move in an anti. And in the southern hemisphere, it's supposed to move in a clockwise sub. Let's move on to the next one. So this is what we have. Choose the correct words from those given in brackets. This one, I want you to pay attention. Before we answer any question, I want to explain this diagram first. Choose the correct words. Choose the correct words from those given in brackets. Write only the words next to the question numbers 1.2.1 to 1.2.7. So this is the diagram that we have, guys. I'm going to explain it first before we attempt to answer any question. Let's not rush. So this is valley climates. That's what should come to your mind. This is valley, okay, climate, okay. This is valley climate. You can see we have got a valley there. That is what? Valley climate, okay. You can also see cooling mountain slope. Of course, we can talk about aspect the other sub, okay. So this is valley climates, okay. So what do we have here? Number one, valley climates. And what time of the day is it? It is during the night. How did I come to that conclusion? I saw the moon here. This is during the night. You have to take note of the clues that are given on the question, okay. So this is during the night. You can see the moon here. You can see the moon, okay. So what happened during the night when the slopes or the earth gives off any terrestrial radiation? What happens? It cooled, the slopes becomes, it's cooled, then it cools the air above it. When the air above it is cooled, what happens? It becomes cold, and cold air by its nature, it does not rise, it sinks. So we have got this cold air, cool, sec, cool air. What is happening? Is sinking, okay. Is sinking or is subsiding, okay. During the night, cool air is cooled off, and as it is cooled off, it's more denser, it's heavier. It starts to what? To descend or to sink, which means here we are talking about katabatic wind. Katabatic wind. Katabatic wind during the night, because we have seen the moon here. There is cold air as well. That is descending, that is sinking, that is subsiding. So that's what we have here. So what do we have as well? you can see as well, as the cold air is sinking, already at the bottom here, the air that is at the bottom is warmer than the one that is sinking. Because when it is sinking, what is happening now, guys, is for every decrease in altitude of 100 meters, of course, I'm going to apply this, the temperature increased by 1 degree. So the sinking of air, it is compressed, then it warms up, okay? Or that's number one. Number two, when it is sinking, it's colder. What is at the bottom is warmer than the descending. So it rises. As it is rising, which means it's going to be trapped now at sea. It's going to be now to be trapped at sea. We have got cold here. Then we have got cold at the bottom. That replaces the one that is rising. So we end up with a thermal belt here at sea. We end up with a what? With a thermal belt. Why? Because whatever was warm has actually been replaced by the sinking cold air. So we have got cold air here, then we have got cold air at the bottom, and the warm air here is trapped. Warm air is trapped, which gives us what we call a thermal belt. Thermal belt. That's what we are going to have. Do we all understand at this point? We want to explain the diagram before we start answering the question. So that's what we have. We are saying the cold or sinking air, of course, as it sinks or subsides, what is at the bottom is warmer than the subsiding air. So it means it goes up, it rises, then it is now trapped by the cold air that is sinking and the cold air at the bottom. Then we have got warm air trapped. That gives us a thermal belt. Are you following? Okay, that is your thermal belt now. So you've got cold air, then you have got warm air that is trapped between cold air above and below. That is our thermal belt. Okay, a thermal belt, of course, we find it mid-slope where warm air is trapped by cold air above and also below. That's why we come up with this thermal belt. All right, let's go to the question now. Do you understand the concept before we start answering the question? Do you understand the concept now before we start answering the question? Do you understand? Of course, it's a form of inversion layer as well, because obviously there's warm air that is trapped there. But this is, and when it comes to, of course, valley climates, that's a thermal belt as well. Okay, sharp. Let's go now. 1.2.1. 1.2.1. Can you see the question clearly? 1.2.1. Air at A cools because of what is the reason for the cooling of air at A? What happens there? Remember, this is during the night. That is during the night. So it's terrestrial. That's correct. Insolation is during the day. That is incoming solar radiation. So our answer there is terrestrial. Okay, that is terrestrial. That's correct. Then number 1.2.2, downward movement of air. Yeah, downward movement of air along the valley slope. Okay, the downward movement of air. We already have our moon here. Downward movement, that should give you a clue as to what is the right answer. Obviously, the cold is during the night. So that is the answer there, during the night. Then 1.2.3, air movement from A to B results in air movement from A to B. Remember, this is cold sinking air that is heavy and dense. That is katabatic. That is correct, guys. You're cooking, guys. You're cooking. Sharp. That is correct. That is your katabatic. Okay, let's move on to 1.2.4. Let me move it closer. 1.2.4, it reads, dew point temperature drops to below freezing point. Where does the dew point temperature drops to below freezing point? 1.2.4. Dew point temperature, obviously at B. And if it goes below freezing point, what is formed when it goes below freezing point? That is B. What is formed when it goes below freezing point? Can you give me the answer? What is formed when it goes below freezing point? That's your frost pocket now. That is your frost pocket. When it goes below freezing point, you have got your frost pocket. Frost pocket, that is the correct answer. It's not radiation fog. It's frost pocket. When it goes below freezing point, when freezing point, below freezing point is mentioned, we talk about the frost pocket. Okay, that's correct. Let's move on to the next one. Precipitation that forms at B when the dew point temperature drops below 0 degrees Celsius is What form of precipitation forms 1.2.5? What forms exactly the same thing when it goes below freezing point? What are we likely to have? That's frost. Precipitation, this way, it just simply refers to various forms of moisture that forms from the sky to the earth. So that is your frost. The moment they mention below freezing point, it's frost. The moment they mention the word below freezing point, what should come to your mind is frost. So the answer there is frost. Okay, guys, don't forget to tap the screen. Don't forget to tap the screen. Guys, don't forget to tap the screen. Let's move on to the next one. 1.2.6. Displays the air from the valley results in air developing at sea. 1.2.6. 1.2.6. What is likely to form? Thermal belt. I can also accept invasion layer. It's fine, but in the thermal belt, because also invasion layer is a form of that a thermal belt as well. I can also accept invasion layer there. That is a thermal belt is correct. Thermal belt, thermal belt, thermal belt. I can accept both. We can accept both, but this is the, okay, I can accept both. Then 1.2.7, layer C is more developed during, layer C is more developed during, is it during the day or during the night? Obviously, our thermal belt is more developed during the night. Of course, we have got two more subsidence, cold air at the top, then also cold air at the bottom of the valley. So it's during the night. That is correct. Let's move on to the next one. All right. We are now moving on to 1.3 now. I'll read. Then we can answer. Okay. Refer to the infographic on tropical cyclone. Eloise. Okay. So the first thing, guys, is we are starting. I want us to analyze the diagram before we start answering any question. What comes to your mind when you hear tropical cyclone Eloise? What comes to your mind? What comes to your mind? What should come to your mind when you hear that tropical cyclone Eloise? What should come to your mind? What should come to your mind? What should come to your mind when you hear the word? Refer to the infographic of tropical cyclone Eloise. I want you to say something about this. Exactly. The cyclones are named alphabetically in the season that they occur. They are named alphabetically. Okay? Named alphabetically. Okay? Alphabetically in the season that they occur. That they occur. Which means it suggests that it's the fifth cyclone. That's number one. That's something that you should take home now. That is the first thing that should come to your mind. Don't rush to answer the question. Analyze the text. Analyze the infographic. So we have said now is the fifth cyclone. Okay, is the fifth cyclone. That's the first thing. Let's move on. Let's start with the description. Tropical cyclone Eloise made landfall on 23 January 2021. 20 kilometers south of Beira in Mozambique as a Category 2 tropical cyclone. Wind speeds up to 160 kilometers per hour were recorded. Tropical cyclone Eloise also caused heavy rainfall with 250 millimeters of rain in 24 hours. Other areas were already flooded ahead of Eloise rainfall, resulting thousands of displaced people. So, from the first description of the disaster, is bringing out the impacts, okay, of the tropical cyclone. That's what we are getting here. We are being told about the impact, okay, and also our tropical cyclone is, we look at it on a scale of what, it's categorized on a scale of 1 to 5, on a scale of 1 to 5. That's why here they're talking about the Category 2. The most destructive in most cases is the Category 4 and 5. But they're saying that it intensified. So from there, what causes the intensification of the tropical cyclone? Number one, when it's within the ocean. Why? Because there's going to be more humidity, there's going to be more evaporation, there's going to be release of latent heat, which actually gives more energy to the tropical cyclone. That's what gives more energy. You understand? So those are some of the things that should come to your mind. We are still talking about the description of the disaster. So it's bringing about the impact. We have heard that number one, strong wind speeds, what is likely to happen, that has been recorded. areas flooded, there are floods also, people were displaced. So this first information that we have here is giving us the impacts. That's what should come to your mind. All right, let's look at the numbers that were affected. The numbers that were affected, at least in numbers. So affected, displaced people, death, these are also impacts. This is also showing us the impact, okay? This is also showing us the impact. Can you see? It's showing us what? The impact. Okay, then let's go now to the movement. Its movement now. How does it move? Okay, check. I'm going to draw a diagram just to explain. Okay, so let's look at this. It moves, okay? I'm going to draw a diagram just to explain before we start answering. There is my circle here. There is my equatorial law. Okay, I'm going to say here at 5 degrees south. Remember, it starts at 5 degrees south or north because at between 0 to 5, there is no Coriolis force. There is no Coriolis force. Coriolis force is responsible for the deflection of wind. In the northern hemisphere, it's deflected to the right. In the southern, it's deflected to the left. So it starts off here. Okay, I'm going to write, okay, the 30 degrees south here. So it starts off here. It's deflected to the left because of our Coriolis force. Then it moves in a southwesterly direction until it reaches this 30 degrees south. That's when it reaches the land where there's more friction, where there's less moisture. You understand? Where there's no latent heat that fuels the movement of our tropical cyclone. So it moves in this direction from 5 degrees south. Why? Because from 0 to 5, there is no Coriolis force. Coriolis force is the force that is responsible for the deflection of wind. In the northern hemisphere, it's deflection to the right. In the southern, to the left. That's why you see it moves from 5 degrees south. Then it moves towards the southwest like this. Okay, so it's still within, let me just say, it's still within the Mozambican channel. It's still within the ocean where there's more moisture, where evaporation takes place, where we have got more latent heat, where there's less friction. So it moves until it reaches the land at 30 degrees south. That's where now it dissipates. That's where now there's more friction. Okay, so if you look at this now, this is the movement, as you can see. This is the movement of our cyclone, which means from here it's moving towards this southwesterly direction. Of course, when it reaches Madagascar, it has reached land, which means there's more friction, there's less latent heat, there's less evaporation, which provides moisture. Okay, so hence it loses power. But however, after that, it goes back to the Mozambican channel. It's going to regain. Why? Because those conditions, the temperatures above 26.5 or 27, you see, all those things now, which means now it's going to gain power. You understand? Then it starts again to be more destructive. Okay? Then what do we have when it gains power? Of course, there's more moisture, more latent heat. Latent heat is released when condensation takes place. So this gives more energy to our moving tropical cyclone. Okay, let's answer the question now. Let's answer the question. 1.3.1. Give one piece of evidence. Give one. Okay, do we understand? Okay, let me just start this. Do we understand do we all understand how I analyzed this diagram, this infographic? If you understand, thumbs up, then we start answering the question now. If you understand the interpretation, is it clear? I can see most of you are fine, okay? I was simply analyzing the information that we have. Let's answer now. 1.3.1. Give one evidence in the infographic that the tropical cyclone is in the southern hemisphere. What evidence is there to support that it is in the southern hemisphere? What evidence is there to support that it is in the southern hemisphere? It's moving in a southwesterly direction, that's correct. Look at the countries, guys. Look at the countries, guys. You have got Mozambique is in the southern. Madagascar is in the southern. Those are some of the things that you can actually use. Beira, all those places are in the southern hemisphere. You understand? All those places are in the southern hemisphere. So all that supports the Indian Ocean, everything, it supports that is in the southern hemisphere. This is more direct Madagascar. In which hemisphere is this? Southern hemisphere. Mozambique is in the southern hemisphere. Indian Ocean in the southern hemisphere. So all this answers the question. Okay, So it's supposed only to be 1. Okay, 1.3.2, state two conditions associated with the tropical cyclone indicated in the infographic. What two conditions are associated with the tropical cyclone that is indicated in the infographic? Remember, here we talked about the heavy rainfall. Here, from the infographic, can you check here? There's heavy rainfall. There's also strong winds. So those are the two things that you can actually pick from the infographic: the gust winds, strong winds, and the heavy rainfall. That is what is associated with the tropical, the tropical cyclone. So the answers are there, guys. There's no reason for you to fail. The answers are there. So you've got the strong winds, you also have heavy rainfall. Let's move on to 1.3.3. Give one reason for the decrease in wind speed on 19 January to 20 January 2021. Here, why was there a decrease in wind speed? Why was there a decrease in wind speed between this period? Choke here is coming from here, it reached Madagascar. Yeah, when it reaches land, when it's over land now, which means there was increased frictional drag. What else? There was decrease in latent heat. You understand? You talk about all those things. Decrease in moisture levels. Those are some of the things that you can actually talk about. Okay. Those are some of the things that you can actually talk about. It has reached land where there's more friction, there's no latent heat, there's no source of moisture. All those things, you talk about them. So that is 1.1.3. We are done with that. Let's talk about 1.3.4. Account for the decrease in wind speed. Tropical cyclone Elise for the increase in speed from 20 to 22. What is the reason behind the increase in speed from the 20 January to 22? Remember, it's back to the ocean now. That's why the wind speed increases. It's now back to the ocean where there is more moisture, where the temperatures are above 26.5 or 27 degrees Celsius, the way there's more latent heat, where there's less friction. So those are the things that you talk about. So whenever we talk about tropical cyclone, you should always know, guys, they ask for what will happen when it reaches land, what will happen when it's still within the ocean. So you should be able to explain. Okay, so obviously, what increased the speed is because there's more moisture, latent heat, less friction, and so on and so on. So that's correct there. Can we move on to 1.3.5? Do you all understand? Let's move on to 1.3.5. Share the live, guys, share the live. Let's move on to 1.3.5. It reads, according to the infographic, negative impacts, according to the negative impact of tropical cyclone Elise are devastating. Okay, suggest 3 strategies that could be put in place to reduce the impact. Okay, obviously we have seen this as some of the impacts. People died, people were displaced, people were injured, infrastructure, houses were destroyed, everything. That's what happened. Areas were flooded. So we are saying, what strategies can we put in place? What strategies can be put in place to reduce the impact? Please, when you are answering this question, take it as a paragraph question. Take it as a paragraph question. Why am I saying that? Because remember, each point you've got 2 marks. So it has to be explained in full. It has to be explained in full. Of course, early warning system, monitoring the development of the tropical cyclone. What else can be done? Early warning systems put in place. What else? Awareness and education programs. Oh, guys, you are cooking, guys, you are cooking. So only 3 points that will be relevant to answer the question. That will be very relevant to answer that question. Okay. Can we move on to the next question, 1.4? Do you all understand? So that we can move on to the next question, that is 1.4. Are you all fine with 1.3.4? Are you all fine with 1.3.4? Yes. Sharp. Let's move on to 1.3.4. 1.3.4 now. What do we have? Refer to the South African synoptic weather map. That's what we have there. This is 1.4. Refer to the South African synoptic weather map. All right. I want us to talk about two things here before we start answering the question. Let's not rush. I don't want us to rush. You should be able to tell whether it's winter or summer. How do you identify the winter season? Let's start with the winter. How do you identify the winter season on a synoptic weather map? How do you identify the winter season? I know, guys, let's not rush. Let's not rush. Let's take the baby steps. I want you to understand before you start answering the question. Don't answer any question. Let's talk about the winter season. How do you identify the winter season on a synoptic weather map? Number one, there's high pressure in the interior, isn't it? High pressure in the interior. There is H. I'll just say H interior. Okay. What else do we have? We have got an approaching cold front. There is a cold front. Okay. There are clear skies. Okay. Clear skies. What else? There is stable weather conditions, which is more like the clear that we are talking about. How about the position of our high pressure systems in winter? What is the position of our high pressure systems? Remember, what happens in winter is, let me just demonstrate here. We have got something like this. Our ITCZ is north of the equator, which means our Kalahari High and South Indian High, they move further north. In winter, this is winter. Guys, don't rush. We are talking about winter now. I see some of you are talking about summer already. Okay, so also here, the Kalahari High, it moves further north. Kalahari High move further north. This is in winter. We have got the high pressure here. We have got clear skies. So you should be able to know how to identify the winter season. So we have said that in winter, the position of our South Atlantic High and the South Indian High is northerly position. Why? Because they are following the shifting of our intertropical convergence zone that is on top of the equator. So that is in terms of position, it moves further far. That's why the mid latitude is able now to affect weather at Cape Town, where now it receive rainfall when it is cold. That's how it's able to affect weather in Cape Town. Why? Because our South Atlantic High is shifted its position following the ITCZ in winter. That's why it happens like that. Okay. So now that we know about winter, let's look at this diagram. What do you think this season is? What do you think this season is? We are looking at the diagram, guys. I was explaining winter season, guys. Now let's talk about this diagram. What season is this? It's summer. That's correct. What evidence supports that it is summer? No, it's not winter. It's summer. What evidence supports that it is summer? What supports that it is summer? We have got an overcast, unstable weather conditions. You can see there is unstable weather condition there. That's why we have got an overcast. The temperature as well. That's correct. That's correct. Overcast, the high temperatures. Of course, what else we have got? We suggest also have the thermal low in the interior there. That's why we have got an overcast. So it means there is a thermal low there in the interior. What else can you talk about? Okay, let's answer the question now. Let's answer the question. 1.4.1, number 1.4.1. All right, the isobars, they are elongated, which is what we call this, the elongation of isobars. What do we call it? The elongation of isobars of the high pressure system. We call it ridging, the ridging of the high pressure system. The isobars, they are ridging. Yes, they are ridging. That's correct. Let's answer the question. Identify the low pressure system A in the synoptic weather map. What is the low pressure system? What is the answer for 1.4.1? What do we call the low pressure in the interior in summer? What do we call it? What do we call the low pressure in the interior in summer? That is your heat low. That is your thermal low. That's correct. Heat low or thermal low. We call it what? Heat low or thermal low. Thermal low. That's correct. Let's move on. Give a reason for the formation of this low pressure system over the interior. Give a reason for the formation. What is the reason behind the formation of this thermal low? We have talked about higher temperatures. What happens? The rising warm air, what does it do? It creates the low pressure. Warm air is what? Is light and less dense. So the moment it's warmed up, it rises. When it rises, it creates low pressure. So we have got higher temperatures and rising warm air creates the low pressure system. The rising warm air creates the low pressure system. 1.4.2. Do we all understand 1.4.2? We are saying higher temperatures is the reason the rising warm air creates a low pressure system. Remember, warm air is light, is less dense. When it rises, low pressure is created. Okay, so the rising warm air creates the low pressure system and the high temperatures. Do we all understand? 1.4.2? Can I move to 1.4.3? Someone is saying, warm air, all right. Warm air is less dense. What does it do? It rises. So the high temperatures that we have in the interior, it warms the air above it. And when it is warmed, what happens? It rises. As it is rising, it creates the low pressure. That's what happened. As it is rising, it creates what? The low pressure. That's what happened. There are higher temperatures. What they do is they warm up the air above it, then it starts to rise, creating the low pressure. That's what happened. Matats, do you get me? Are you getting me? We are saying the higher temperatures, it warms up the air above it. When it's warmed up, warm air, what does it do? It less dense, it rises. As it is rising, low pressure is created. Matats, do you understand now? So that I can move on to the next question. Do you understand, Matats? You are saying, I don't understand. Is it clear now? Higher temperatures, warm air, less dense, it rises. As it is rising, it creates the low pressure system. Okay. Matlatse, just respond. You were saying you don't understand. I don't want anyone to be left behind. I'm disagreeing with you. Say, all right. Let me try to, okay. What is happening? What do we have in the interior where we have got the thermal law? We have said the temperatures are what? The temperatures are high in the interior. High temperatures, warm air. Warm air is less dense. What does it do? It rises. When it rises, low pressure is created. That's how the thermal law is created. There's someone who's saying, I disagree with you. Say, there is warm air that rises. When it rises, low pressure is created. Even when before we even start this topic, remember, when we compare your cold and the warm air, your warm air is associated with what? The low pressure system. Low pressure system, how is it formed? When warm air rises, okay, low pressure is created. That's basically what we are talking about. We are saying for number 2, there is what? Higher temperatures. Look at 28 degrees. Look at this 30 degrees. It's higher temperatures. Those higher temperatures, what does it result in? Warm air. Warm air is less dense. Hence, it rises. When it rises, that's how a thermal law is formed. That's basically what we are talking about. Warm air, as it rises, low pressure is created. Are we together, guys? I want us to agree before we can move on to the next question. I don't want to put some of these things under the carpet. If you agree with what I've just explained now, just the thumbs up so that we can move on. Thumbs up, thumbs up. Warm air rises. Yes, when warm air rises, low pressure is created. That is it. That is the simplest definition, the simplest explanation. I've said warm air. Warm air is less dense, it's light. It rises. When it rises, then low pressure is created. That's basically what we are talking about. Sharp. Let's move on. Thank you. Give evidence from the synoptic weather map that the South Atlantic high is reaching. 1.4.3. What evidence is there to show that it is reaching? What evidence is there to show that it is reaching? That the South Atlantic high is reaching. What evidence is there? There is elongation of the isobars. You can see they are extending towards the thermal low, the low pressure in the interior. There is elongation of the isobars. That's what shows that it is reaching. There is elongation of the isobars. Do we all understand my explanation for 1.4.3? There is elongation of the isobars. They are extending towards the low pressure that is in the interior. That's what we call elongation of the isobars. Is it clear? 1.4.3? Or there's someone confused? I don't want anyone to be left behind. Is it clear? Is it clear? Just a thumbs up if you are fine. Thumbs up. If I can get about 10 thumbs up, then I know that we are on the same page. To someone saying confused, please repeat. We are saying now, when you look at this South Atlantic high, the isobars, they are elongated, extending towards the interior where we've got the low pressure. So this is what we call ridging of the high pressure system. Okay, that is the evidence that shows that it is ridging. They are elongated, moving towards the low pressure. Remember, our wind moved from high to low. Okay, so it's elongating towards the low pressure in the interior. The elongation is what shows, of the isobars, is what shows that the high pressure system is ridging. Is it clear now? So that I can move on to the next one. Is it clear? 1.4.3, elongation, which means they are extending towards the low pressure. That's elongation. That's what we refer to as ridging. You can see here, they are elongated, moving, extending towards the low pressure, the thermal load there. That's what we call ridging. That's the evidence, is elongation of the isobars. Okay, 1.4.4. Why does the ridging of the South Atlantic result in onshore winds? So I want us first, before we answer this question, okay, what is the difference between onshore and offshore winds? What is the difference between onshore and offshore? Onshore and offshore. What is the difference between onshore and offshore winds? What is the difference between onshore and offshore? Before we answer this question. Onshore, from the ocean to the land, or from the sea to the land. Offshore, from the land towards the sea. Exactly. Onshore, from the ocean or from the sea towards the land, then offshore, from the land towards the ocean. So you have to know the difference between the two, because otherwise, if you don't, then you're going to make a mistake. Know the difference between offshore and onshore. Okay, so I can see most of you know from Bubu, you said onshore is from ocean. It's not ocean to ocean, ocean to the land. That is your, okay, let me just fix something here, just a minute. All right, sharp, we are back, guys, we are back. I was just fixing something. Okay, so our offshore, we have said that it's from the land to the sea, that is offshore. Onshore, from the sea towards the land. Okay, so why, what does the, why, which means you need to give the reason why. If you see this way, the ridging of South Atlantic results in onshore winds. What is happening? Remember, we have got something like this. This is what? Our high pressure. It moves in an anti-clockwise. Check where I'm drawing with my pencil, which means it's coming from the Atlantic Ocean going towards the land. So it's moving in an anti-clockwise from here going towards the land, which means it's coming from the ocean towards the land. That's what makes it onshore. This is our high pressure, our anticyclone. So it moves in an anti-clockwise from the Atlantic Ocean towards the interior. So there's anti-clockwise circulation. That's the reason now that you are giving now. There is an anti-clockwise circulation. This is South Atlantic high. It moves in and what? In the southern hemisphere, in an anti-clockwise. So the anti-clockwise circulation, it means it's coming from the ocean towards the land. That is the reason there. Anti-clockwise circulation of high pressure. It's also ridging. The ridging is from the ocean towards the interior. So do you understand? Do you understand question 1.4.4? Do you all understand question 1.4.4? If you understand the way I've explained it, please thumbs up if you understand. Remember, it's an anticyclone high pressure system. It moves in an anti-clockwise. It means it's moving, check my pencil, the way I'm showing here, from here to the interior. So it's anti-clockwise from the ocean to the land. That's why we are saying now it results in onshore winds. That's because of its movement from the ocean towards the land in an anti-clockwise circulation in the southern hemisphere. That's what is happening. All right, let's move on to 1.4.5. Describe the weather conditions. Describe the weather condition in Port Elizabeth as a result of onshore winds. What is happening in Port Elizabeth as a result of onshore winds? Let's go. Where do we have PE? Of course, is pointing here. The results in Port Elizabeth as a result of onshore winds. What is happening there? There is precipitation. You can see it's overcast there. We are likely to have precipitation, which means there's a precipitation in the form of rainfall, because you can see this is the weather condition. It's overcast. So there is precipitation. What else? There's overcast conditions, increasing humidity. So you talk about what you can see. Guys, you can see this is a weather station model. It's overcast, likely chances of rain. There's a symbol that is here. So you talk about what you are seeing. This is what is likely to happen at Port Elizabeth. This is what you are seeing on this diagram. That's what you are supposed to talk about. Okay, so we have said first one, there's precipitation in the form of rainfall. What else? Increasing humidity. What else? So those are some of the things that we can actually talk about. Someone is saying 1.4.4. There's someone who's saying, say what? The 4 marks 1.4.4. Okay, 1.4.4, the 4 marks is coming from number 1. We have said that there's an anti-clockwise circulation. Number 2, we have said that there is the ridging extends towards the land. The ridging from the ocean is extending towards the land. You get your 4 marks. Or you can say elongation of isobars towards the coastline. So you get your 4 marks from any 2 points. 1.4.4, someone was asking me. Okay. Are we fine, guys? Are we fine? Are we fine with 1.4.4 and 1.4.5? So that we can move on to 1.5. Are we fine? Are we fine? Are we fine? No one is supposed to be left behind, guys. Here we simplify things. That's why we call ourselves simplified FETGO. We simplify things. We simplify things. Okay, let's move on to 1.5. 1.5. What do we have? One of my most interesting concept, okay? Refer to the infographic on the South African dark wind. On the South African dark wind. Please repeat 1.4.5, all right? Someone is saying I should repeat 1.4.5. Describe the weather conditions. Weather conditions at Port Elizabeth as a result of onshore winds. Someone is saying 1.4.5 is not a problem. Remember, guys, no one is supposed to be left behind. So we are saying when you look at this weather station model, you can see that there's an overcast there. Can you see? It's likely to have precipitation in form of rainfall. Overcast, that's point number 1. The second point is what? We are saying now we are likely to have rainfall because it's overcast. Overcast is 1 point. Second point, we are likely to have rain. You can see the sign here of rainfall. So you get your 4 marks. Is it clear now? 1.4.5, is it clear? Is it clear? 1.4.5? I hope it's clear now. Can we proceed to 1.5? Just thumbs up if 1.4.5 is clear. Someone is saying no. Guys, this is the weather station model of Port Elizabeth. Okay, the question is saying describe the weather conditions of Port Elizabeth as a result of onshore winds. This is PE, Port Elizabeth. This is the weather station model. What do we have? Overcast, number 1. Number 2, rain. Look at this symbol. Look at this symbol. If you want to ask, type your question there, then I can read. I'm looking at your comments as well. So we are talking about the overcast. We are also talking about the rain. There's likely possibility of rain that we are likely to have there. Okay. Is it fine now? 1.4.5, is it fine so that we can proceed? There's someone was saying, clarity seeking question on the weather station model. On the weather station model, what shows the wind direction? All right. So when you look at this then, okay, wind direction here, check here. We name the wind from where it's coming from. This one is a southeasterly. Southeasterly. Can you check here? This one, you can see this is 10 knots. Southeasterly, where it's coming from. That is, we name from where it's coming from. That is southeast here. that is 10 knots. Okay, this is your air temperature, 20. This is your dew point temperature. All right, someone is saying clarity seeking question on the weather station model. What shows us the wind direction? Here, that is where it's coming from. We name from where it's coming from. Southeasterly, north, south, west, east. Is between south and east. It's coming from the southeast. Is it clear now? Is it clear now? There's someone who was asking, who's this? It's Miss Molly. Is it clear now? If it's clear, thumbs up, guys, so that we can proceed. Remember, we've got 2 papers that we are supposed to cover. Can we proceed to 1.5? Let's proceed to 1.5. Thank you. Thank you, guys. 1.5. 1.5 now, it reads, refer to the infographic on South African berg wind. Refer to the infographic on South African berg wind, okay? That's what we are doing. Let's read. First, let's analyze the diagram. Guys, whenever you have got a question paper, don't rush to answer the question. Let's analyze. You will see that after our analysis, answering the question becomes easier. Let's look now at the record-breaking heat wave. Here's East London, Matthew Field. Let me read. Okay, East London residents were subject to sweltering heat last Saturday after a record-breaking heat wave resulted in peak temperatures of 43.9 degrees Celsius. According to the South African Weather Service, the heat wave was a result of bad wind condition when hot, dry winds blow down the coast from the country's high central plateau. So if you look at this, guys, already, if you look at this, what we have been given here, this is already defining or explaining what berg wind is. You can look at this way. They said when hot, dry winds blow down the coast from the country's high central plateau. Already says something that has to do with the berg winds. Okay, that's what we can actually deduce from this. It is also associated with the strong winds. It is also associated with the higher temperatures. Those are some of the things that we can actually take home. Those are some of the things that we can actually use in answering our question. Okay, what else do we have? We can see, if you look at this diagram now, what do we have? We have got the coastal low here, the L here. They are likely to ask about it. Coastal low. What else do we have? In the interior, what else do we have? We've got a coastal low, that's what I can see. Even if you can see the condition that are in the interior, we don't have an overcast. It's more like, yeah, I would say clear skies. Of course, it's not an overcast, you can see. I know it's not that visible, but from what we are seeing here. Then lastly, these are the temperatures that we are seeing. Okay, the temperatures, trends, differences in terms of temperatures during the course of the day. All right. So the question now reads, name 2 pressure systems that are necessary for berg winds to develop. What 2 pressure systems are necessary for the berg winds to develop? Or before we do that, let me explain something. So what we are saying, guys, is like this. This is a mountain. All right. So berg winds is like mountain winds. Okay. That's basically a berg mountain African. So we are saying now, these are dry gust winds that blow from the interior where we have got our Kalahari towards the coast. Okay. In winter season. So you have to define them in terms of where it starts or it's coming from the interior where we have got the high pressure, that is your Kalahari high, towards the coast where we have got the low pressure. So what happens when it is descending down the mountain? It is adiabatically warmed, which means for every decrease of 100 meters, the temperature increased by 1 degree. That's why you see, we can say maybe there's 20 degrees here. There, it can be, let's say, 35 degrees Celsius. Why is it that we end up with higher temperatures at the coast? It is because as it is descending, it is compressed and it heats up, which means the temperature increase with a decrease in altitude, what we call adiabatic warming. We call that adiabatic warming. In some books, they call it dry adiabatic lapse rate, which means for every decrease in altitude of 100 meters, the temperature increased by 1 degree. That's what is happening on the side where we have got the berg winds. That's why we end up having problems such as veld fires. Why? Because as the air is descending, On this side, that is the leeward side, it is compressed and warmed up, which means now it results in higher temperatures here at the coast where we can have veld fires. That's part of your back winds. Okay, let's answer the question now. Name the two pressure systems that are necessary for back winds to, okay, 1.5.1, 1.5.1, 1.5.1. What is the answer there? 1.5.1. Let's communicate, guys. Let's communicate. I can see now you are kind of silent. What's the answer there? 1.5.1. 1.5.1. What is the answer for your 1.5.1, guys? 1.5.1. Name the two pressure systems that are necessary for back winds to develop. What are the two pressure systems? What are the two pressure systems? We have got what? 1.5. We need the Kalahari High. Kalahari High and the coastal low. These are the two pressure systems that we need. We need the Kalahari High and the coastal low. These are the two things that we need. The Kalahari High and the coastal low. That's what we need. The Kalahari High and the coastal low. That's what we need. The Kalahari High and the coastal low. That's what we need. Okay. Are we together, guys? Kalahari High and the coastal low. Those are the two things that we need. If you are fine, can you give me a thumbs up? If you are fine with 1.5.1. Thumbs up, guys, so that we can proceed. 1.5.1. Sharp. Determine the highest temperature that was recorded on 31 March 2021. What was the highest temperature recorded? What was the highest temperature recorded on 31 March 2021? What was the highest temperature that was recorded there? Okay, can you see here? The answer is in the infographic, 43.9. Make sure you write, 43.9 degrees Celsius. I'm talking about this, 43.9. 43.9 degrees Celsius. This is what was recorded, 43.9. Thank you. Then the next one, what role did the escarpment play in increasing the temperature of the back winds between 10 to 2 o'clock? What role did the escarpment play? What role did the escarpment play? What role did the escarpment play? What role did the escarpment? Remember, it's going down. This is part of the escarpment. What role did it play? What role did the escarpment play? We are looking at number 1.5.3. What role did the escarpment play? Remember, there is increased heating. Why am I saying that? Because for every decrease of 100 meters, the temperature increased by 1 degree. I'm talking about this question, guys, 1.5.3. Can you see it? 1.5.3. 1.5.3. Can you see it? 1.5.3. Adiabatic heating, that's correct. For every decrease in altitude of 100 meters, the temperature increased by 1 degree. There is adiabatic heating, increased heating. That's correct. That's correct. 1.5.1, someone is asking, is the Kalahari High and the coastal low. That is 1.5.1. 1.5.1 is the Kalahari High and the coastal low. Those are the two systems. Kalahari High and the coastal low. Then, do you all understand 1.5.3? We have said that increased heating due to vertical distance of the escarpment. Increased heating due to the vertical distance of the escarpment. We have talked about adiabatic warming or heating. What else? The escarpment have got a greater vertical height. The escarpment have got a greater vertical height. So you can get your 4 marks from there. Are we fine with 1.5.3? Thumbs up if you are fine. 1.5.3, if you are fine, thumbs up. Okay, 1.5.3, guys, is saying what role did the escarpment play in increasing the temperature? This is part of the escarpment. Remember when I was explaining here, part of the escarpment number 1, adiabatic heating or dry adiabatic lapse rate. That's number 1, which means for every decrease in altitude of 100 meters, the temperature increased by 1 degree. You can also talk about the escarpment has a greater vertical height. The greater vertical height, this elevation, which means as the temperature, as the height, the altitude decrease. For every 100 meters, the temperature increased by 1 degree. That's basically what we are talking about. Then you get your 4 marks. Is it fine? Is it fine, guys, so that we can move on to the next question? Thumbs up if it's fine. Thumbs up, thumbs up. Yes, 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 yes. Let's move on to 1.5.4. In a paragraph of approximately 8 lines, explain the impact of bad winds on the physical natural environment. Guys, this is a paragraph question. Here, guys, I want you to pay attention. I want you to pay attention on 1.5.4. The best way to answer the paragraph question is to explain your point in full. Fact and qualifier, fact and qualifier, fact and qualifier. 4.2, 4 by 2, 8 marks. You can only get the 8 marks if you explain your point in full. Okay. So impact, explain the impact the bad winds conditions will have on the physical environment. Remember, it's on the physical environment, on nature, the physical. So don't say anything that has to do with the social or economic. It's the physical environment. What are likely to be some of the problems? Let's talk about the strong winds. What do you think will be the impact of the strong winds to the natural vegetation? What do you think will be the impact of the strong winds to the natural habitats? What do you think will be the impact of higher temperatures to vegetation? It's likely to dry out. You understand? You're looking at all those things. Reduction in terms of biodiversity. What do you think will the impact to the soil moisture because of higher temperature, which means there will be a decrease in soil moisture. So you are commenting on the natural environment, the physical environment. You don't have to include anything social, anything economic. You don't have to include it. You are focusing on the physical environment. That's what you are doing. So you look, your point should, don't talk about the crops, because crops are grown. Crops is not part of nature. You grow crops, you plant crops. We are looking at the physical environment. The moment you mention crops, guys, it ceases to be the physical environment. Crops is out because you plant crops. We are talking about the physical environment. It can cause vet fires, okay? Which can vet fires obviously is going to affect the natural habitats. Is going to affect biodiversity, is going to affect the ecosystem. So 1.5.4, please don't say anything that has to do with crops, because crops are planted. It's not part of the physical environment. Crops is not part of the physical environment. Okay, wildfire results on habitat species destroyed, that's correct. Natural disasters, okay, such as, given examples, animals, be specific, wildlife animals, as in animals, okay, what will happen? Obviously, they're forced to migrate. Some of them can even die. You understand? Cause respiratory problem, obviously, to the wildlife, okay? The physical environment, focus on the physical environment, guys. Don't lose focus. The physical environment, the strong winds can uproot the vegetation, natural vegetation. Pollution, no. Pollution, how? Be specific there. Physical environment. Add more information on your pollution so that it's more clear. Otherwise, you end up getting a half or 1 mark. So let's try to be as precise as possible. Are we all fine? Are we all fine? I want us to move to the other paper. I want us to do first. Okay, let's go to geomorphology, I think. Let's go to geomorphology so that if it happened that we won't be able to finish, then we would have covered everything. Can we move to geomorphology now? Are we all fine? If you are fine, please, let's move to geomorphology. Thumbs up if you are all fine. Thumbs up. Yes, 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 yes. Danko. Geomorphology. Wow. Question 2, geomorphology. Let's check now. Geomorphology. Various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D. I want to say something. About this, the longitudinal profile. Point X, Y, and Z shows the different stages, causes from the source to the mouth. I want to explain the diagram. Can you give me time to explain this diagram? All right, I'm fast. Okay, I'll try to slow down, guys. All right, so we are starting off with geomorphology. I'm going to explain what is on the diagram now. I'm going to explain this diagram in detail. Then we can start answering the question. So, number one, when you see something like this, which shows this the profile of the river from the source to the mouth, what should come to your mind is it is a longitudinal profile. Longitudinal profile, it's showing you from the source. The source is where the river starts. The mouth is where it ends. So our longitudinal profile is divided into three courses. Our longitudinal profile is divided into three courses. We have got the upper course. What do we have in the upper course? Let's talk about the upper course. In the upper course, in terms of gradient, it's very steep. Since it's very steep, it means now we have got more erosion in the upper course. To be specific, the type of erosion that we have in the upper course, we have got vertical erosion. That's what is more dominant in the upper course. So in the upper course, it's very steep in terms of gradient. There's more vertical erosion, and also the river is more erosive. It has got more energy. It has got more energy. Some of the landforms that you are likely to have in the upper course is your waterfall. You are likely to have your rapid. Type of flow that you're likely to have is a turbulent. Your turbulent. We are likely to have an ungraded profile because there's a lot of nick points such as your waterfall, your rapids. So here we are likely to have an ungraded profile. Why? Ungraded profile. Why? Because the rate of erosion is more than the rate of deposition. We are likely also to have a gorge there. A gorge, okay, in the upper course. So these are some of the things that you get within the upper course, okay? In the middle course, there is more of lateral erosion, which is side-to-side erosion in the middle course. This is your middle course. So there is more of your lateral erosion, which is side-to-side. What it does is it increases the width. It increases the width of the river. It erodes from side to side. In the upper course, it's more V-shaped. Why? Because here there's more vertical erosion. So here it's U-shaped. Why? Because there's more lateral erosion in the middle course. In the middle course, we have got more of lateral erosion. But we can also say we have got meanders. In some of the landforms, we can have oxbow lakes. We can have braided stream. We can also have natural levees and so on and so on. Okay. But here, in terms of gradient, it's also sort of gradual. It's gentle just a bit. V-shaped, this is what we have in the upper course because there's more vertical erosion in the upper course. V-shaped, there's more here, which means this is going to give us what we call a transverse profile or a cross-section profile in the upper course. It's V-shaped like this because there's more vertical erosion. Then in the middle course, it's sort of U-shaped. Why? Because there's more lateral erosion. Okay. Then here in the lower course, what do we have? We have got deposition that is taking place. There is more of deposition because the river has lost most of its energy. The river has lost most of its energy, so there's more of deposition. We are likely to have a laminar flow. What else? We are likely to have landforms such as your deltas, your flood plains. We can also have meanders here and oxbow lake. So in short, this is what you can have. Someone is asking, what is a gorge? What is a gorge? These are just deep valleys. 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 That's what we refer to as gorge. Okay. So do you understand my explanations here? Natural levees, of course, which are raised banks, you can find them in the middle course and also part of the lower course because there is also deposition that is taking place. Okay, is this clear, guys, the explanation that I've given? Is it clear? All right. Let's go through the question, then we can add some of the things, guys. We don't want to end up doing something that is not related to what we are supposed to do. I'll explain all those things, the waterfall, the floodplain, I'll explain. That's why we are here. Okay, so do you understand here? Here we are saying now, guys, we have got this longitudinal profile of a river. In the upper course, there is more vertical erosion. That's why we end up with this V-shaped cross-section, because vertical erosion increases the depth of the river. It increases the depth of the river. It deepens the river. That's why it's V-shaped. Okay, so in the upper course, it's very steep. So it means the water is flowing at a faster speed, which is what we call higher velocity. We have also said that the profile that we are likely to have in the upper course is ungraded because there is more erosion than deposition. We have also said that we are likely to have waterfall, rapids. We are also likely to have a turbulent flow. We are also likely to have gorges. These are some of the things that we have in the upper course. In the middle course, we have said that we have got more of lateral erosion, which is a side-to-side erosion that increases the width of the river. We have talked about lateral erosion. We have said that we have got meanders, Oxbow Lake, braided stream, natural levees in the middle course. Some of these fluvial landforms, you find them in the middle and lower course as well. Then we also said that in the lower course, we have got more deposition, which means now the river has lost most of its energy. Now it starts to deposit some materials. We are likely to have more of a laminar flow. There we have got deltas, we have got floodplains, we have got meanders. We also have Oxbow Lakes. That's what we have said. Any questions before we start with the questions? Any questions? Any questions? Any questions? Any questions? Should we proceed? Should we proceed? So you are fine, Mus. You are fine. You are fine. Let's answer the question now. Some of these things we add, but let's answer the question first. We don't want to mix things, okay? The profile from the source to the mouth shows, what does it show? The profile from the source to the mouth, what does it show from the options given? 2.1.1, what is the answer? The profile from the source to the mouth. It shows the length. That's why we're calling it the longitudinal profile from the source to the mouth. So the answer there is B, which is your longitudinal profile. It's B, it's not depth, guys. Depth is not depth, it's length from the source to the mouth. It's showing the length. It's not D, it's the length. The answer is B. Are we all fine with 2.1.1 so that we can move to 2.1.2? Anyone confused? Anyone confused? Sharp. Let's move on. 2.1.2. The stages course is represented by XYZ. Which stages is represented by XYZ? What do we have? What is the correct answer? X. Which course is X? Yeah, that is C. That is the upper X, Y, middle course, Z, lower course. The answer is C. Then 2.1.3 describes the river valley at X. What describes the river valley at X? Number 2.1.3. What is the answer? 2.1.3. The river valley at X. What is the answer there? 2.1.3. It's narrow and deep. Narrow and deep. Narrow and deep. Remember, in the upper course, there's vertical erosion. That's what makes it narrow and deep. We are talking about this. We are talking about this. It's narrow and deep. It's not wide. It's narrow and deep. Narrow and deep. So the answer there is D. It's narrow and deep. Is there anyone confused with 2.1.3? Anyone confused so that I can explain? No. X is here. Okay, sharp. Are you all fine? Danko. Let's move on to 2.1.4. It says at Z the river is a laminar flow due to what is causing the laminar flow at Z now? 2.1.4. What is causing the laminar flow? We have seen the diagram, guys. Laminar flow, obviously, we expect there to be gentle and also even, isn't it? We expect gentle slope and even, which means our answer is C. I see some of you have already indicated that. Then 2.1.5, I'm going to go back now. Slope T, we didn't talk about that. Let's look at this. 2.1.4, I want you to look at the screen here. Can you check there? It's showing you the cross-section of a meander. The cross-section of a meander. When you talk about the meander, guys, there are two things that you are supposed to know. In the outer bank, there is erosion, which results in an undercut slope. In the inner bank, there is deposition, which results in a what we call the slip of slope. So when you are looking now at this diagram, can you see the direction in which it's flowing? Which one is your outer bank and which one is your inner bank? Which one is your outer bank and which one is your inner bank between S and T? You can see it's coming from this side. Which one is your outer bank? So it means T is your outer bank. Out, this is in. There is erosion here. Okay? Here is outer. Here is what? Inner. Here there is erosion. Here there is deposition. So you are supposed to know. You are supposed to know, guys. Outer bank. So if you are to draw it now, it's supposed to look like this. S, T. So it's gonna look more or less like this. Okay. Why? This one at T, where you've got your erosion is deeper, where you've got your deposition is shallow. So it's gonna be like this. That is where you've got your T, that is where you've got your S. That is your cross-section of your meander. Outer bank, here there is erosion. This is undercut. This is slip of slope. Okay, let's go to the question now. 2.1.5, what is the answer now? Slope T on the meander is the 2.1.5 is the undercut slope. So the answer there is undercut slope. That is the answer. Do we all understand? Undercut. Then 2.1.6. Slope S on the meander is associated with, what is it associated with? Slope S on the meander. 2.1.6, what is the answer? What is the answer? Number one, we take it out. Remember, there is deposition there. We cannot talk about deposition where there is steep gradient. So A is out. B, we cannot talk about gentle gradient and erosion is out as well. Are you following? 2.1.6. This one is out as well. The correct answer there is there because it's shallow. It gives you more of a convex and deposition. So the correct answer is what? Is D. Anyone confused with 2.1.6? The difference between concave and convex, concave is like this. Is steep, then gentle. Okay, that is concave. This is concave. Convex is gentle, then steep. This is convex. Okay, that is the difference. Concave is this one. Steep, then gentle. This one is gentle, then steep. This is your concave. This is your convex, gentle, then steep. That is the difference between the two. So the correct answer there, we have said that is D, 2.1.6. Do we all understand 2.1.6? Anyone with a problem with 2.1.6? Anyone with a problem? Let's move on to 2.1.7. 2.1.7. The narrowing of the neck of the meander is eventually form N. What is formed as a result of the narrowing of a meander? 2.1.7, you have an Oxford leg. You will have an Oxford leg. That's correct. Then 2.1.8, the meander will migrate dash on the flat plane. 2.1.8, the meander, what will it do? Remember, it's in the middle, because laterally. Laterally. Remember, there is a side to side, so it's likely to do it laterally. What causes the meander in the middle course? Because of lateral erosion. So the answer there is laterally. Laterally, which means from side to side. That's how it's able to go laterally, is side to side erosion, okay, which increase the width. Can we proceed to the next one? 2.2.1. Are you fine with this? Any questions on what we have covered? You all fine? You want me to explain this? Someone is saying explain. What do you want me to explain? 2.1.8. We have said laterally. Upstream. Do you know what happened when the waterfall is cutting back to the source? That is upstream. Downstream. 2.1.6. 2.1.6 D. 2.1.6 we have said is D. 2.1.6 convex slope and deposition, because it's shallow. Can we proceed? Can we proceed? The concave part is coming when we are looking at it as being deeper, because when it's convex on the other side, it's sort of shallow because there's more deposition. It's not like concave is always associated with erosion. Remember, when you talk about concave profile, we are talking about when the rate of erosion deposition is in equilibrium. That's how it maintains that concave or graded profile. So that's what we are saying. Let's proceed. Thank you. Next one. Refer to the sketch which shows the waterfall with a plunge pool. Complete the statements in column A with the columns in statements in column B. All right. So let's talk about the diagram. Let's talk about the diagram before we answer any question. Let's analyze the diagram. This is the technique I want to instill in you. Whenever you are answering the question, do not rush. Start first by analyzing the diagram. You analyze the diagram. You analyze the diagram first. So you analyze the diagram. Sorry, I was just getting some water. You analyze the diagram first. What do we have? Number one, we have been told that it's a waterfall. What should come to your mind is this is the upper course. Upper course of the river. It's a fluvial landform that is formed in the upper course. That's what should come to your mind. Okay? That's the second thing. All right. So let me explain how a waterfall is formed. That is the first thing that I want us to do. I want to explain how a waterfall is formed. Then we can proceed. The first thing is we have alternating hard and soft rock. All right. I'll take this as soft. All right. Our river is flowing in this direction. Okay. This is hard rock. I want to show you how we got to this diagram. This is hard rock. This is soft rock. Okay. So when our water is flowing here, it means now the rocks that we have, alternating hard and soft rock, they've got different resistance to erosion. So this one now, it eroded slowly as compared to the soft rock. So when the water is coming now, it erodes, it starts to erode the softer rock here that is underneath the resistant rock. So it continues to what? To erode to a point whereby this resistant rock, okay, will be left as an overhang. So what it does is it will definitely collapse into this plunge pool that is formed here. But when this is happening, it's retreating upstream, it's cutting back to its source. It's cutting back to its source. That's why you see this diagram now. Because when it's eroding what? The softer rock, the plunge pool is formed because whatever is left as an overhang, the resistant rock, it actually gets plunged into the plunge pool. Okay, are we together? So that's how we end up with something like this, because obviously it's cutting back to its source through headward erosion that we call backward headward erosion, cutting back to its source. So we have got a plunge pool, we have got hard rock and soft rock. The hard rock is eroded slowly as compared to the soft rock. So when the soft rock is eroded, it means that the hard rock cannot stand on its own. What does it do now? It's going to fall into the plunge pool because it does not have any support. So it continued to retreat upstream through headward erosion that we call backward headward erosion. So that's how the waterfall cut back to its source. It continues migrating upstream. It is because of that, through headward erosion, that is a form that we call backward headward erosion. It continued to actually erode backwards upstream. That's what happens. Okay. Let's answer now. Waterfalls formed when? 2.2.1. What will be the answer there from the options given? Where does it form? The answer is X. You can see there's hard and soft rock alternating hard and soft rocks. Then number 2, waterfalls are likely to be found. In which course are we likely to find the waterfall? Remember, I mentioned that when we started. 2.2, of course, it's Y, in the upper course. Then 2.3 refers to the softer rock that erodes faster. Which one erodes faster? Which one erodes faster between these? Look at this key. Which one erodes faster between A and B? It's A, because A is the softer rock, okay, which is X. Then the plunge pool is formed by, what forms the plunge pool? 2.2.4. 2.2.4. What forms the plunge pool? What forms the plunge pool? That is your what? 2.2.4. That is your erosion. That is your erosion, okay? Then when the softer rock at sea erodes, it will cause, what does it cause? The softer rock at sea, when it erodes, 2.2.5, what does it cause? When the rocks at sea, what does it cause? 2.2.5, that is your X. It collapses into the plunge pool. Okay. Then 2.2.6, the retreat of the waterfall will result in the formation of, what does it form? 2.2.6. What does it form? What does it form? Of course, you guys are cooking. That is your gorge. Then the last one, an advantage of a waterfall. What is the advantage of the waterfall? What is the advantage of the waterfall? 2.2.7. What is the advantage of a waterfall? X. That's correct. Hydroelectricity. Hydroelectricity. Any questions? Any questions? I think you are fine. Can we move? Thumbs up. Can we move on to 4.3? Can we move on to 4.3? 4.3 sharp. All right. Refer to the diagrams below showing drainage patterns. Okay. Drainage patterns. Guys, we have got different drainage patterns. Can you list, okay, can you write for me the different types of drainage patterns that you know? Can you write them down there on the comments? Not these ones, just in general. Just in general, the drainage pattern, the different drainage pattern. I'm not talking about these ones only. I want the different types that you know. Okay, rectangular, deranged, trellis, parallel, centripetal. There's also centripetal. Thank you, guys. You know your things. Okay, let's get to the question now. So we have got these two types of drainage patterns. Okay, can you identify the two drainage patterns? I want to show you something. Can you see here? Adapted from https www.google.com trellis and dendritic drainage pattern. So if they are going to ask you the drainage patterns that are here, you already have the answer. It's here. Can you see that? That is a trellis. And your dendritic, can you see there? Can you see there? It's even written there. So every information is very important. It's even written here, trellis and dendritic drainage. Someone is saying rectangular, we'll talk about that. So there is a trellis and dendritic. It's even written, you are given here. Adapted from https www.google.com, search trellis and dendritic. So your A is what? Your A is trellis. That is your trellis. This is your dendritic. Are we fine with this? Let's move on to 2.3.2. 2.3.2, differentiate the underlying rock structure of the drainage pattern A. Where is the trellis common underlying rock in terms of underlying rock? It's common where we have got alternating layers of hard and soft rock. Alternating layers of hard and soft rock for A. For our trellis, we are saying it is common where we have alternating layers of hard and soft rock. Thank you, that's correct. Or a folded rock structure, that is for your trellis. That's correct, folded sedimentary rocks. How about the dendritic? Dendritic, how about dendritic? How about this one? How about this one? We are now talking about the rocks with a uniform structure. That's correct. Uniform resistant to erosion. That's correct. Let's move on to 2.3.3. Why are the tributaries of the main stream parallel to each other in the drainage pattern A? Why are they parallel to each other? Why are they parallel to each other? Why are they parallel to each other? We are doing 2.3.3 now. The tributaries, these ones, why are they parallel to each other? They flow in relation to the folds of the rock. They flow in relation to the folds of the rock. Of course, the hard and soft as well, it also applies. They flow in relation to the folds of the rock. Okay. What else? The stream flows over soft rock of the syncline valley. Of course, that's how we respond to that question. 2.3.4, determine the stream order at 1 in the drainage pattern B. The stream order. Determine the stream order at 1. I'm going to do the stream order. Of course, we have got 1, 1, 2. 1, 1. We have 2. 1, 1, 2. 2, 2. It gives us 3 here. Then 3, 2. We have got 3. 1, 1. It gives us 2. 1, 2, 1. We have got 2. 1, 1, 2. 1 and 2. We have got 2. 2 here. We have got what? 2. 2 and 2. We have got what? 3. So at 1 is third order. Third order. This is third order. Do you understand third order stream? That's correct. Let's move on to 2.3.5. All right, someone is saying, how do we count them? All right, no problem. I want you to check here. Can you see what I've done? The first one is the first order. Order 1 and 1. The numbers has to be the same. Then they give you the next higher number. 1, 1. You are not adding. It's 1. Order 1 and 1. It gives you the next higher order. 1 and 1 gives you second order. 2 and 1. It remains 2. I follow. Then 1 and 1, 2. So where they meet here is third order. That's how we get to the third order. Are you following? 2.3.3, why are the tributaries of mainstream parallel to each other in the drainage pattern A? 2.3.3, we are saying that the streams flow in relation to the folds of the rock. They flow according to the folds of the rock. And remember, it is made up of hard and soft rock as well. So this is what determines the angle at which they flow. This is what determines the angle at which they flow, which is at right angle. Okay. Which is why they are parallel as well. They flow according in relation to the folds of the rock. Is it clear now? All right, let's move on to 2.3.5. Choose the correct word between the brackets to make the statement true. The higher the stream order, dash the drainage density. The higher the stream order, dash the drainage density. 2.3.5. What is the answer? What is the answer there? Exactly, is the higher. Okay, the higher the stream order, the higher the drainage density. I want to explain drainage density in about 5 minutes. I want to explain drainage density in about 5 minutes, then we can answer the question. So when you talk about drainage density, guys, drainage density, okay. When you talk about drainage density, guys, this is the total length of streams per unit area. That is your drainage density. So there are two concepts that explains our drainage density. Okay, we have got number one, surface runoff and infiltration. Okay, so I'm going to divide this into two: higher drainage density and lower drainage density. So we are saying drainage density is the length, total length of streams per unit area. So we are saying now, where we have got higher drainage density, there is more surface runoff. Where we have got higher drainage density, there is more surface runoff, which results in more streams flowing. So higher drainage density, here there's more surface runoff. Okay, so where we have got more surface runoff, we are going to have a higher drainage density. So what causes higher drainage density? Number one, let's say steep gradient. What do we mean by that? We are saying now, on the steep slope, the water is not allowed to settle. So as soon as it rains, it starts to flow, which means we have got more surface runoff, which adds more water to the streams, already existing streams, or more streams. So we have higher drainage density where the gradient is steep. That's number one. Number two, where we have got less vegetation or no vegetation. We are saying now, when we receive rainfall, the ground is compacted so that infiltration is reduced. Then we have got more surface runoff. So where we have got no or less vegetation, it means that we are likely to have more surface runoff, which result in more streams flowing. So less vegetation or no vegetation result in more surface runoff, which results in higher drainage density. Number three, we can talk about the type of rock, hard or resistant rock. We are talking about hard or resistant rocks or impermeable rocks, which means where we have got higher drainage density, we are not saying it does not allow water to pass through it. The rocks are hard or resistant. Hence, we are likely to have more surface runoff. That results in what? Higher drainage density. On the other side now, where we have got low drainage density, there is bound to be more infiltration. More infiltration. What encourages more infiltration? Number one, dense vegetation. Okay, what do we mean by that? When we have got dense vegetation, it means now the water, okay, is intercepted by the tree leaves, so that when it gets to the ground now, it has got more time to infiltrate. So we are saying now dense vegetation encourages low drainage density because there's more infiltration. Porous rocks also allows water to pass through them, which means obviously it results in more infiltration, which is lower drainage density. What else can we talk about? Gentle gradient. Water is allowed to settle. As it settles, it means we have got lower drainage density. There's more infiltration. So that's what is happening. I don't know, guys, do you understand in general? I just wanted to simplify the concept of drainage density. Do you all understand so that we can proceed? Is there anyone with a problem with drainage density? We have defined it. I have explained it. So we are fine, right? Let's answer the question now. Let's answer the question. All right, someone is saying I'm confused. What is confusing you? We don't leave people behind. We don't do that. We simplify things. Someone is saying I'm confused. Okay, you're fine then. Refer to drainage pattern B and describe the relationship between drainage density and low rainfall. A. What to be the relationship between drainage density and low rainfall? 2.3.6. Lower rainfall, it results in what? Lower drainage density. Lower rainfall results in lower drainage density. So here we are going to have lower drainage density. Less streams will flow because we do not have a lot of rainfall. Lower drainage density. So here drainage density and low rainfall. We are saying where we have got low rainfall, we are likely to have a lower drainage density. Are you following? Is there anyone confused? Lower rainfall, lower drainage density. Because less streams are going to flow. That's what we are talking about. Yeah, sharp. Then how about drainage density and steep gradient? Steep gradient, remember, water is not allowed to settle as soon as it rains. It means now we are going to have more streams flowing. So here we are going to have a higher drainage density. Drainage density. So density, drainage density and low rainfall, we are likely to have a lower drainage density because less streams will flow. But where we have got drainage density and steep gradient, when it's steep, which means it encourages surface runoff, which results in what? In higher drainage density. Do we all understand 2.3.6? Do we all understand 2.3.6? You can't see. All right, sorry. Do we all understand 2.3.6? Sorry, guys. Of course, I've made it more visible now. Can we proceed to 2.4? Someone is asking some steep slope. Steep slope, more surface runoff. What do you want me to explain? Okay, we have said that drainage density and low rainfall. Where we have got low rainfall, we are likely to have less streams flowing, which results in low drainage density. Low rainfall, low drainage density. Why? Because we haven't received a lot of rainfall. Hence, less streams will flow. That is A. Drainage density and low rainfall, we are likely to have a lower drainage density. We are likely to have a few streams flowing. That results in lower drainage density. So when we have got steep slopes now, we are saying water is not allowed to settle. As soon as it rains, there is more surface runoff, which adds to the amount or the number of streams flowing. So drainage density and steep gradient, higher drainage density. Then drainage density and low rainfall, lower drainage density. Is it clear now? Is it clear? Can we proceed? Is it clear now? Thank you. All right, let's move on. We are now moving on to this one. Refer to the diagram of floodplain. Refer to the diagram of floodplain. All right, let's just talk in general. Remember, guys, the technique that I've been showing you, I think from when you started. So what should come to your mind when you're looking at this diagram? Number one is, of course, you've got your floodplain, you've got your cultivated land. So what should come to your mind now is, obviously, at some point, the floodplains, they are associated at one point or other with some fertile soils. You understand? Because there is alluvium that is deposited when the river is in flood. That's why we are having the cultivated lands where we have got our floodplain. Number one is in the lower coast. Of course, that's where there's more deposition. That's what should actually, it should come to your mind. Lower coast. Okay, there is more deposition. There is deposition of alluvium on the plain, okay, on the sides of the river, which makes the soil to be fertile. You understand? Which makes the soil to be fertile. That's why we are not talking about the cultivated land, because the alluvium is deposited on the floodplain. So, which means agriculture can actually take place there because the soil is fertile. That's something that should come to your mind as well. Obviously, areas that are close to the river, they are prone to floods as well. You understand? So those are some of the things that you should actually think about. Okay, so let's answer the question now. 2.4.1. State the geomorphological process that gives rise to the formation of floodplain. What causes floodplain? The geomorphological. What causes the floodplain? That is your deposition. Deposition. Some sediments are deposited there. It's a deposition. That is the geomorphological. The geomorphological process that gives rise to the formation of floodplain. We are saying now, when the river is in flood, obviously it carries with it some heavy material. Some of them are soluble, some are insoluble. So some of these, when they are heavy, they are deposited on the plain. That is side of rivers. Okay. When they are deposited, okay, that's how we're ending up having this floodplain. This is the river. This is on the side of the river. That's basically what we are talking about. Okay. Describe the gradient at X. It's gentle. This one is gentle. Okay. Oh, sorry. You can see. All right. So are we fine with 2.4.1 and 2.4.2? Are we fine? Are we fine with 2.4.1 and 2.4.2? Thumbs up if you are fine. Someone is asking, why gentle? Can they be deposition on the steep slope? Can they be deposition on the steep slope? It's gentle. That's why we are able to farm. That's why some of this material are deposited. It's gentle. That's why deposition is able to take place, because it's gentle. If it was steep, obviously this was going to be moved. You understand? It's flat. It's gentle. You understand? Okay, sharp. 2.4.3. Yes, it's 1 mark. 1 mark is 2 marks here. It's 1 point for 2 marks. Check here. 1 by 2. That point is 2 marks. 1 by 2, which means the only 1 point is what they want, but it's worth 2 marks. Okay. Let's move on to 2.4.3. State 2 reasons. State 2 reasons for the wide floodplain at X. What could be the 2 reasons? In short, they are asking you how it was formed. What are the 2 reasons for the wide floodplain at X? What could be the reason? What can you write there? 2.4.3. There is increased deposition of alluvium. Increased deposition of alluvium. You can talk about low volume of water, of course. Obviously, this is on the... can we talk about erosion, guys? Can we talk about erosion? There's more of deposition, guys. Let's not talk about erosion. Low volume of water, which is out in deposition. Many tributaries deposit sediments. That's what we can talk about. Let's take out erosion. It's not relevant there. Erosion is not relevant. Regular flooding in the area. What could be the possible explanation for the formation of this floodplain? That's basically what they're asking about. Remember, we have said that the dominant process there is deposition. That's why we have got the floodplain. When the river reaches the bankful, of course, bankful stage, it's more of your natural levee there. Let's just say in general, increase the deposition of alluvium on the floodplain. That could be one reason. River is shallow, resulting in more deposition. Anything that encourages deposition is what has resulted in this floodplain. Is it fine? We need only 2 points there. Can we proceed? Regular flooding in the area, that's part of your rainfall. Regular flooding in the area, it can cause also these floodplains. Okay. We have said that regular flooding in the area. We have said also many tributaries deposit sediments, increased deposition of alluvium. That's what we have said. So we have got increased deposition of alluvium on the floodplain. River is shallow, resulting in more deposition. Many tributaries deposit sediment. Regular flooding in the area. These are some of the things that you can include to answer that question. Then 2.4.4. In a paragraph of approximately 8 lines, explain the physical, natural impact of flooding on the floodplain. The physical, natural impact. What could be the physical, natural impact? What could be the physical, natural impact of flooding on the floodplain, what will happen? What are the changes, the physical impact of flooding on the floodplain? What will happen as a result of floodplain? As a result of flooding in the floodplain, what will happen? Deposition of what? Of silt or alluvium increases the width of the floodplain, which means there's going to be continual deposition of alluvium, which is going to increase the size of the floodplain. Continual deposition of alluvium, which is going to increase the size of alluvium. You can see yes, more. So if there's continual flooding, which means there's going to be more alluvium deposited, which increase the size of the floodplain. What else can we talk about? It also increases soil moisture content, which supports vegetation. It also increases soil moisture content, which actually supports vegetation or improve biodiversity. What else can you talk about? The biodiversity of the floodplain also increases. The biodiversity of the floodplain also increases. We are talking about the natural, okay? Alters, adapt the changing conditions. What else can we add? What else can we include? What else can we include? I want to hear from you guys. I've got the answers with me, but I want to hear from you as well. It also creates wetlands. It also creates wetlands, increases, yeah, that's correct, habitat for eco-organisms, that's correct. What else? It also creates wetlands, which are habitats for living organisms. Fertile soils, that's correct. We have got 2 points now. What else? We want 4. We want 4. What else? It creates wetlands, which are habitats for living organisms. That's number 3. What is the other one? We want 4 points at least. Continuous flooding, it purifies water or improves water quality. Soil will be fertile. Okay, what else? Okay, I think we have had enough of that. Okay, let's move on to the last part, guys. 2.5. 2.5, river capture. Then we call it a night. River capture, then we call it a night. All right, what do we have? Sorry, my camera is moved now. Refer to the sketch of river Y and Z before river capture has taken place. So, before river capture, we have got the key. Take note of the key. We have got the watershed. We have got, okay. So, what do we have, guys, here? We have got 2 rivers here. River Y and what? River Z. Okay. So between these 2 rivers, the other one is energetic, the other one is less energetic. That's what we have. Which means when you look at the 2, you would find that your river Y is the more energetic, which will capture the headwaters of a less energetic, that is your Z. That's what will happen. So what is going to happen is there's going to be upstream, okay, this river is going to erode backward, headward erosion backward through the watershed. It's going to erode backward through the watershed up to the point whereby it's going to capture this less energetic river Z. So that's what is happening. So it's a matter of knowing what river capture is. River capture, this is when a more energetic river captures the headwaters of a less energetic river. That's what will happen. So when it comes to river capture, you need to know the before river capture and after river capture. You need to know the 2. What happens before and what happens after. What happens before and what happens after. Okay. So let's answer the question now. Define the concept river capture. What is river capture? This is when a more energetic river captures the headwaters of a less energetic river. When you're looking at the 2, you can see that this one is your more energetic river. That is your river Y, and your Z is your less energetic river. So this is before capturing. Okay. Are we fine with 2.5.1? Are we fine with 2.5.1? Thumbs up if you are fine. 2.5.1, if you are fine, just a thumbs up. 2.5. This is the question, 2.5.1. Define the concept river capture. River capture, this is when a more energetic river captures the headwaters of a less energetic river. River capture, this is a process where a more energetic river captures the headwaters of a less energetic river. That's what river capture is. This is when a more energetic river captures the headwaters of a less energetic river. Are you following? River capture, this is when a more energetic river captures the headwaters of a less energetic river. Can we proceed? Please, guys, don't forget to tap the screen. Guys, don't forget to tap the screen. As we'll be doing this, don't forget to tap the screen. This is when a more energetic river captures the headwaters of a less energetic river. Don't just say when one river. You have to specify that a more energetic river captures the headwaters of a less energetic river. Please try to make sure that you do that. 2.5.2, please, guys, don't forget to tap the screen. State one condition needed for the river capture to take place. What is needed for the river capture to take place? For 2.5.2, what is needed? More rainfall is needed. We need more rainfall for the river capture to take place. That's one condition. What else? Less resistant rock on the watershed so that it can be able to erode upstream. That's another thing. High volume of water. What else is needed? Okay, we can take those ones. It's only 1 point that is needed there. Soft rock at the watershed. Now, sharp. Then 2.5.3, draw a sketch to illustrate an area after river capture. So after river capture, we are going to have something like this. All right. We are going to have something like this. This is our river. This one now, what it has done is it has captured this. Then we have something like this. We have got RY. We have got RZ. This one is a misfit. This one is a wind gap. Wind gap. This one is an elbow of capture. Elbow of capture. Okay, so this is what you're likely to have. This is what you're likely to have. We are saying now this river have cut through the watershed so that it captured the river Z here, giving us an elbow of capture, wind gap here. Then we have got a misfit there. That's what is needed. That's what our question asking for, elbow of capture, misfit. All right. So do we understand? Are we all fine with this? The after capture. If we are fine, let's just put the thumbs up. Let's put the thumbs up if we are fine so that we can proceed to the next question. Thumbs up. Thank you. Please don't forget to tap the screen. Sharp. Will river Y or Z experience rejuvenation? Let's define what is river rejuvenation. What is river rejuvenation? 2.5.4. Let's define it first. What is river rejuvenation? What is river rejuvenation? What is river rejuvenation? We are doing 2.5.4 now. 2.5.4. We want to define first what is river rejuvenation. What is river rejuvenation? What is river rejuvenation? What is river rejuvenation? This is when a river becomes more energized and it starts to erode vertically. So you have to include those two. The river has got more energy now, then there is more downward erosion that is taking place, or it starts to erode vertically. This is a process whereby the river regains its energy or becomes more energetic and it starts to erode vertically. That is your rejuvenation. You have to understand the concept, okay? You have to understand the concept. What is river rejuvenation? This is when a river becomes more energized and it starts to erode vertically. That's basically what it's all about. You have to make sure that you include all that. It becomes more energized. So what is the answer now? 2.5.4. Will river Y or Z experience river rejuvenation after river capture? Which one is going to be rejuvenated? Which one is going to be rejuvenated? It's river Y, because it's the more energetic river that has captured the less energetic. So the answer there is river Y. What we have here, guys, which river has been captured? This one is the capture one. It has captured this. Which one is going to be rejuvenated? River Y is the one that is rejuvenated. River Y. Anyone confused with that? Anyone confused with that? Is it clear? If it's clear, just give me a thumbs up. If it's clear, if you all understand, agree that is River Y, give me a thumbs up. All right, sharp. Give a reason for your answer in question 2.5.4. What could be the reason why you say it's going to be rejuvenated? What could be the reason? 2.5.5. 2.5.5, what could be the reason? Because it has got increased volume of water. Remember, it has captured this less energetic. So now it has got more volume of water. River Y has got more volume of water, increased volume of water. That's why now it has been rejuvenated. It has more volume of water. That's how it has now been rejuvenated. Okay, sharp. Let's do the last one. Refer to your answer in question 2.5.5 and explain the impact of the change in the capture stream. What will be the impact of the change? Here, this is your capture stream. What is the changes that are going to take place on Y? What changes are going to take place on Y? What changes are going to take place on Y? What are we likely to have on Y? What are we likely to have on Y? High volume of water, that's correct. High velocity, that's correct. High volume of water, high velocity, increased volume of water. What else? What else? What else? What else? What else? High velocity of water. What else? What else? The meanders can become more incised. The meanders can become more incised. When you're talking about an incised meander, to incise is to cut deep, more vertical erosion. There can be increased flooding because of the greater volume of water. What else? I think we have said enough there. We have said enough there. Boys and girls, I think we have done justice. All right. Let's go through MapWork. Let's go through MapWork. I think we are done. Let's just go through MapWork. Just a few questions on MapWork. Yo. Some of you are writing tomorrow. Let's just go through a few questions on MapWork. Please, guys, don't forget to tap. Don't forget to tap. Don't forget to tap. Let's go through a few questions on MapWork. Tell me if you are ready. I want to go through MapWork now. The last part, MapWork. Tell me if you are ready. Please, guys, don't forget to tap. Don't forget to tap. Tap the screen. Tap the screen. Can we start with MapWork now? Can we start with MapWork? Can we start with MapWork? All right, sharp. All right, let me give you 1 minute break. Just go to the toilet. Just 1 minute, then we can start with MapWork. I'm timing you now. It's 17 past. Let's start at 19 past. Just go to the bathroom. 19 past, just 2 minutes. Then we can start with MapWork. 2 minutes to go to the bathroom. Just 2 minutes. Just 2 minutes. 19 past we start. Just 2 minutes only. Two minutes to go to the bathroom, then we can start. 2 minutes to go to the bathroom, then we can start. We are starting with our MapWork. Please, if you are there, just tap the screen, tap the screen. Yeah, just a minute, then we are starting. Just a minute, then we are starting. Tap the screen, guys. Tap the screen whilst you're waiting for this. Gifts are also welcome. Tap the screen, tap the screen. The diamonds and everything are also welcome. All right. Let's start now. I think you are back. Let's start now. All right. So when you are doing MapWork, guys, I want you to take note of this. Guys. it is very important that before you start, I've got the map of Palaborwa. Let me just check it. I've got the map with me here. I know you don't have a map there, but I'll try to make sure that I explain this in detail. This is the map of Palaborwa. Okay, so when you are doing map work, guys, what is important is start with the general information. Don't rush. Read this information. You might find some of the things that will answer your question. So some of you, I don't know why you rush. You want to, there's no trophy of finishing first. So you're not going to be given a trophy that you are the first to finish. No. Go through the general information. That's what you're supposed to do. Let me just read here. So the coordinates, you might come across a question that asks about the coordinates of Palaborwa. It's here. So let's just go through it now. It reads, Palaborwa is a town in Limpopo, South Africa. It is located near the confluence of Gaselati River and Olifants River along the western border of the Kruger National Park in the Lowveld. Tourism and wildlife play dominant roles in the life of this town. Attractions such as Blythe River Canyon, the three rondavels, God's Window, Boxlack, potholes, and river cruises on the Olifants River make Palaborwa an important tourist destination in the province. So what you can pick from this background information, number one, is the province where it is located. That is Limpopo. That's one thing you can pick. So you can be asked about that. Let's go, guys. I don't want to waste your time. In which province is Palaborwa? You see what I was talking about. In which province is Palaborwa? In which province? Obviously, what is the answer there? Limpopo. That is in what? Limpopo. All right, sharp. Then 31 in the map index. All right, I'm going to explain this. We have got 2331 CC. I'm going to explain this. I know some of you. So here is the explanation. Here is the explanation. So your 23 is the latitude. 23 is the what? Latitude. 31 is the longitude. This is your 31 is the longitude. So when they are doing maps, they divide the grid into 4 bigger blocks. That is like this: A, B, C, and D. So the C that you have on 2331 is the bigger block. Is this one? Is this block? Is this block? This is the block. That is the C that you have. That is, this is a bigger block. Okay. Then they further divide these blocks again into 4 for each block, which means we are going to end up with something like this. In A, we have got A, B, C, and D. In B, we have got A, B, C, and D. In C, we have got A, B, C, and D. In D, we have got A, B, C, and D. So it means when you are looking at your map now, 2331CC, 2331CC is this box. So that's why when you look at your map, it says an extract from. You understand? Which means it's only this part, which means this map was taken from this bigger map. That's why they said an extract from 2331CC, Palaborwa. An extract from. So which means this is the only part that is shown on your map. That is your 23 latitude, 31 longitude, C bigger block, and C smaller block. That's what this means. We call this map reference. So this is what it means. 23 is latitude, 31 is longitude, C bigger block, and C smaller block. So this is the area that is shown on the map, which is 2331CC. That's what is shown on the map. All right, let's continue now. 31 on the map index refers to 3.1.2. What is the answer? 3.1.2. What is the answer? Give me the answer for 3.1.2. What does 31 represent? What does 3.1.2? 3.1, it represents the longitude. Remember I said latitude, longitude bigger block, then smaller block. So 31 represents the longitude. The answer is A. Anyone confused with that? Anyone confused? Anyone confused? Are we fine? Okay, let's move on. What is the map index? What is the map index? Southwest of 2331 cc. So let's look at where our 2331 cc. Which map is southwest? Remember, north, south, west, east. So which map is, what should I repeat? Guys, you should pay attention, guys, because otherwise we won't be able to finish, and it's getting late now. I have said that when you're looking at your map, this one, 2331 cc. 23, it represents the latitude. 31 is the longitude. C, the first letter C is the bigger block. Then the last letter C is the smaller block. How did I explain that? I drew this. This is 23 latitude, longitude. Then I had 4 bigger blocks, A, B, C, D. Then I further divided my A into 4 bigger blocks, smaller blocks, in A, B, C, D, in B, A, B, C, D, in C, A, B, C, D, in D, A, B, C, D. Then I identified this as my 2331 cc. Okay, so on this number, which is your map code, 2331, 23 is latitude, 31 is longitude, C is bigger block, and C is smaller block. Is it clear now? Is it clear now? Can I proceed? Thumbs up so that I can proceed. Can you put a thumb? Okay, sharp. All right, let's do 3.1.3. What is the map index southwest of 2331 cc? So 2331 cc is here. Here is here. Let me highlight it. Is here. So this is your north. This is your west. This is your east. This is your south. So which map code or index is southwest of, all right? So this is northeast. This is southwest, this is northwest, this is southeast. So which map code is southwest of 31 cc? Which map code? What is the answer then? What is the answer? What is southwest of 2331 cc? It's what? 2430 BB. This one. 2430 BB is what is on the southwest. 2430 BB, 2430 BB, which means this is the answer. C. Are you following? Sharp. Let's move on. Calculate the area covered by 6 on the D4, D5, D4, the area covered by them. Feature 6. All right. This is the feature. It's on the topographical map. Calculate the area covered by the feature 6 on the D4, D5, on the orthophoto map in square meters. So what you need to take note of is, what are you calculating? The area covered by the feature what? 6. Area covered by the feature 6. Where? D4, E4, and 5. On which map? Orthophoto. Your answer is supposed to be in what? In square meters. Are you following? On this first part, are you following first? Let's start with that one. Is there anyone confused with that part, or you are fine? Thumbs up if you understand the question. All right. So it's saying now, use the following information. Measured length is 2 centimeters, which means you have already been given the length. What is your calculation is length times breadth. So area is equal to length times scale times breadth times scale. They usually give you this, length times breadth, but you're supposed to multiply your length times your scale and your breadth times your scale. That's what you're supposed to do. And take note, your answer is supposed to be in square meters. And we are using what? We are using an orthophoto map. What is the scale of the orthophoto map? 1:10,000. This is in centimeters. let's convert those centimeters, the scale of an orthophoto to meters so that we make our life easier. Which means I'm going to divide the 10,000 divided by 100. I'll get 1:100 what? Meters. Okay. So this is the feature here. We have already been given the length, which means from here up to there is 2 centimeters. From here up to there is 2 centimeters. From here up to there is 2 centimeters. We have already been given, which means from there, this is the longest side. We have already been given. There's no need for us to measure it. We are only going to measure the other side, which is the breadth. Let's measure now. Okay, so we have measured it. Check here. We have got something like, I'm seeing 1.1. Not 1.1. Sorry, man. Sorry. Not 1.1. I'm seeing 1.6. That's what I'm seeing here. 1.6 centimeters. That's what I'm seeing. Do you all agree? 1.6 centimeters. That's what I'm having here. 1.6 centimeters. So we have got now our breadth is 1.6 centimeters. So how are we going to multiply it? The answer here is the formula is length times breadth. So what is our length? Our length is 2 centimeters multiplied by. We have said that we want our answer in square meters. So we are going to multiply by 100. Then we say 1.6 centimeters multiplied by 100 meters as well. All right. Do you understand this stage here? 2 centimeters multiplied by 100 meters in brackets, 1.6 centimeters multiplied by 100. Do you all understand this stage? If you understand, please a thumbs up. Then so that we can move on to the next stage. Thumbs up. No, I don't understand. This is the question, measured length. We have got 2 centimeters already. So we have measured the breadth. That is from here up to there. Here up to there, we have got 1.6. Okay. So we are now saying our length, which is 2 centimeters, we are multiplying it with the scale because we want our answer to be in square meters. We have changed our scale of the orthophoto. We have changed it from centimeters to meters, which is 1 centimeter on the map represents 100 meters on the actual ground. That's why we are multiplying our 2 centimeters, which is the length. We are multiplying by 100 meters in brackets. Then our breadth, which is 1.6, we are multiplying by 100 meters as well. Do you understand this stage so that we can move on? Do you all understand, guys, so that we can move on to the next stage? Can we proceed? Please don't forget to tap the screen sharp. So we are saying now 2 by 100, 2 multiplied by 100. What do we have? We have got 200. So it means we are going to have 200 what? Meters. Then 1.6 by 100, 1.6 multiplied by 100. We have got 160. That is 160 meters. Do you understand this stage? Do you understand this stage now? Where I am now? We have got 200 now by 160 meters. Do you understand this stage? Thumbs up if you understand. Sharp. So let's multiply now our 200 multiplied, 200 multiplied by 160. 200 multiplied by 160. What is the answer? We have got 32,000. So this is our answer, which is what? 32,000 square meters. That is our area. This is our area. Do you understand? The answer there is 32,000 square meters. So in each and every stage, what have I done? I made sure that I write this in full, that we multiply our length times the scale in brackets, our breadth times the scale in brackets as well. Then you make sure you use the correct units of measurement. If you write 2 by 100, it's wrong. Write 2 centimeters multiplied by 100 meters in brackets, then 1.6 centimeters multiplied by 100 in bracket. That's another stage that's supposed to be done that way. Then you multiply your 2 centimeters by 100 meters. You take the unit of measurement of the actual distance that we get from the scale, which means you have got your 200 meters. Yeah? Multiplied by, if you multiply your 1.6 by 100, you got 160. If you multiply the 2, you have got your 32,000 square meters. That's how you do it. Is it clear? Can we proceed? Give me a thumbs up if it's fine so that we can move on to the next one. Thumbs up if it's fine. Guys, don't forget to tap the screen. Don't forget to tap the screen. Sharp. We are moving on now to 3.1.5. 3.1.5 say, why does feature 6 appear larger on the orthophoto map than on the topographical map? So to answer this question now, 3.1.5, remember, the bigger the number, the smaller the scale. The bigger the number, the smaller the scale, which means our topographical map is a small scale map. The smaller the number, the larger the scale, which means our orthophoto is a large scale map. I have answered your question. So it means the scale of the orthophoto map is 5 times larger than the scale of the topographical map. A orthophoto is a large scale map. That's basically what we are saying. An orthophoto is a large scale map. That's basically what we are saying. Hence, it appeared to be larger. So we are saying that the scale of the orthophoto map is 5 times larger than the scale of the orthophoto map. Is it clear? Can we proceed? Thumbs up if it's fine. If it's fine, thumbs up if it's fine. All right, let's move on to the next question. Determine true bearing. We are going to do true bearing now. Determine the true bearing from spot height 445. All right, let's identify this. Which map are we using? We are using a topographical map. So the first thing is we are calculating true bearing from spot height 445. Where is our spot height 445? This is where our spot height 445 is. Can you see here? 445 here to spot height 421. So we have got these two given points. This one 445 and 421. So whenever we are calculating true bearing, we need to have 2 points. The 2 points that we have, the other one, you go where it says from. Remember, it said from spot height 445. This is the from. This is the 2, the 421. So you go where it says from, which is 445. You draw a straight line that passes through that 445. This is what I did here. Why do we do that? We want to identify the true north because we measure our true bearing in a clockwise from the true north. Clockwise. So which means we measure from here. We are supposed to draw a perpendicular line that passes through 445, which is the from point. So that's what we have done. Second thing, we join the 2 points, the from and the 2. Spot height 445 and spot height 421. So here we are going to measure the angle clockwise from the true north, which means we are now going to take our protractor. This is the protractor. We measure from the true north. I'm going to place my protractor here. Can you see? There is my protractor from 445. Straight line is going to give me what? 180 to start with. Straight line is going to give me 180. So I'm just going to say 180 degrees. But I'm not yet done because this is a straight line. So I'm going to do this. I'll tilt my... all right. Then I'm going to measure from this line that I've drawn. Can you see here? 0, 0, line is somewhere around 10 degrees. So I'm going to add this 10 degrees from 0 to 10 because I'm measuring from here. The straight line gave me 180. I'm going to add this 10 degrees now. Can you see? I'm going to add the 10 degrees now. That's what I'm going to do. So I've got 180 here plus 10 degrees. So that is going to be my true bearing, which is 190 degrees. Do you understand? If you understand, please give me a thumbs up. I've got 190 there. If you understand, give me a thumbs up. Sharp. So please do it again. Come on, guys. Come on, guys. We have got 2 given points. We are measuring our true bearing from spot height 445. So you identify 2 given points. The from is 445. The 2 is 421. You draw a line, perpendicular line that passes through 445. Why do you do that? You want to identify your true north because that's where you measure your true bearing from. So I've drawn this line that passes through 445, which is the from point. Then I've written TN, which is my true north. Then the second thing, I join my 2 points, the from and to. That's what I've done, 445 and 421 spot height. Then after that, I'll take my protractor. I'll measure from the true north like this. I'll place my protractor here. So which means the straight line is giving me 180. That's why I've written 180 here. Okay, then I'll take my protractor again. I'm measuring the remaining angle here, which is from here to this line that connects the other point. I've got 10 degrees. So I'm adding my 180 plus 10 to get what? 190 degrees. Are we all fine now? Is it fine now? It's fine now. I think it's fine now. It's fine now, guys. Let's proceed. Otherwise, we won't be able to finish sharp. Then the question now reads, the magnetic declination for 2021 is 17 degrees 10 minutes west of true north. That is the MD. Use the true bearing in your answer to calculate the magnetic bearing. So what is happening now, guys, is this paper is a 2021 paper, which means in that year, this was the current MD. This was the current magnetic declination for that year. Remember, when we are doing the magnetic declination, we use the current. So there's no need for us to calculate the difference in years, to calculate the total annual change. There's no need if you have got a question like this. Why am I saying that? I'm saying this because we are already given the current magnetic declination for that year. So what we are going to do now, for our magnetic bearing, we say true bearing. What is our true bearing that we got? We got TB plus MD. What is our true bearing? It's 190 that we got, plus what is our magnetic declination? I'm going to call it the current because it was in that year in 2021. It was what we are just going to add because it has already been calculated. We are given the current for 2021. This is a 2021 paper. So we are just going to add. That's why here we are just going to add 17 degrees 10 minutes west of true north. Write it like that. Okay. Then you add the two to get your magnetic bearing. How are you going to do it? You are now going to say 190 plus 17. You don't add the minutes. The minutes you are going to add them on their own. Okay. So we are going to get something like 207 in terms of your degree. So your magnetic bearing now will be 20710 minutes. Your magnetic bearing doesn't have any unit. You just write it like that. So your answer there, your magnetic bearing will be 207 degrees 10 minutes. That will be your answer. Is it clear? Is it clear, boys and girls, so that we can proceed? Thumbs up if it's clear. Thumbs up if it's clear. We want to finish, guys. It's getting late now. Thumbs up if it's clear. What is not clear, guys? Be specific. What is not clear? Because here, what do we have? It's saying the magnetic... Remember, this is a 2021 paper. So it was the current magnetic declination for that year. Where is the 170 now? I don't remember having 170. This is 207. 207, 10 minutes. I have added the true bearing, 190, plus the magnetic declination for that year, which was the current MD. That's how I got the 207. The question reads, okay, let me go back to the question. The magnetic declination for 2021, it was the current year. Okay, so it was already calculated. That's why we just add our true bearing plus the current that we are given. Can we proceed? Oh, the marks that are here is 1 for 3.1.7. It's 1. There's 1 mark here. There's, okay, let me make it more visible there. Okay, can we proceed? Guys, come on. Like, seriously? Someone is asking where I get the true bearing. Guys, you should pay attention, guys. Otherwise, we are not going to finish. I need to rest as well, guys. Let's proceed. All right. So 3.2, refer to the seasonal rainfall graph and the topographical map of Palaborwa. So this is what we have. In which season is the lowest rainfall in Palaborwa? In which season? You can see there's more rainfall in what? Which season is it? Can you give me the answer there? In which season is the lowest rainfall experience in Palaborwa? In which season? December is not a season, guys. December is not a season. June is not a season. Please. In which season? Not month. In which season? December is not a season. June is not a season. In which season is the lowest rainfall in Palaborwa? So if you say June is wrong, because June is not a season. So the answer there is winter. Is winter. B, identify the type of river that show that the mapped area receives seasonal rainfall. The type of river. What type of river shows that the mapped area receives seasonal rainfall? What type of river? What type of river? You can see is the dashed. Is the dashed blue line. That is, it's not episodic. Come on, guys. Episodic on a map. It can't be episodic. Episodic only flows as soon as it rains. It's non-perennial or a periodic or a seasonal river. Please, it's not episodic. Episodic is a river that flows as soon as it rains. So it's periodic, it's seasonal or non-perennial. You can see with the dashed blue lines. That's what shows you that it's seasonal. So it's non-perennial. Then C, can we proceed? Can we proceed to 3, to C? State one strategy in block A2 that has been implemented to overcome water shortages. In A2, what has been put in place to overcome water shortages in A2? What do we have in A2? A2, what do we have in A2? What is this? We have a dam, isn't it? Or you can say perennial water. Dams or perennial water, that is your answer. You get it from that diagram, okay, from the map. We have got in A2, we have got this, a dam. Or you get perennial water or just a dam, sharp. Then 3.2.2, the wind direction in block B4 and C4 on the topographical map. Wind direction in block B4 and C4. Let's see, wind direction in block B4. All right, we have got this landing strip. All right, we have got this landing strip. Okay, B4 and what? B4 and C4. Wind direction, we have got this length. Yeah, it has something to do with this. Okay, then the question reads, is either north, northwest, or south, southeast. Give evidence from the blocks above to support this statement. 3.2.2. What supports this statement? The orientation of your land strip here. That's why we are saying it's either northwest or what? South, southeast. It is because of this landing strip. That's what supports the wind direction, the landing strip. The landing strip. This is the question, 3.2.2. Sorry, read the question 3.2.2. Then I'll show you the map. The wind direction in block B4 and C4 on the topographical map is either north, northwest, or south, southeast. Here, we are talking about where we have got this landing strip, B4 and C4. This is the landing strip for the aeroplane. So we are saying it's either north, northwest, or south, southeast. It is because of we are able to determine the wind direction because of our landing strip here. Because of a landing strip, that is the answer. The orientation of the landing strip. Planes take off and land according to the prevailing wind direction. The planes, they take off and land according to the prevailing wind directions. That's the answer there. Is it clear? So that we can move on. Thumbs up if it's clear. Thumbs up if it's clear, sharp. Then landform 7 in block B4, B1 on the orthophoto. Landform 7 on block B1 on the orthophoto. What is it? Landform 7. What is landform 7 in block B4? What is landform 7 on block B4? Landform 7 on block B4. What is it? Check here on the options. I'll show you again. Landform 7 on block B4. What is that landform? That is a saddle. You find it between these two. That is a saddle. Okay, that's correct. The answer there is D. That is a saddle. Then the feature F in block C5 on the topographical map. Feature F on block C5. Feature F on block C5. What feature F do we have? All right, what is this feature on block feature F? What is this feature? Where two streams meet. What do we call it? Feature F. We call that a what do you call it? A confluence. Where two tributaries join. That is a confluence. Can you see? Feature F. That is a confluence. Which means your answer is what? Is B. That is confluence where two tributaries meet. That is your feature F. Okay. We are almost done. Let's move on. Match landform 8 in block C1 in orthophoto with the correct freehand cross section. So what we have here at 8, can you match it with the correct freehand? 3.2.5. This one, can you see? Remember, I think in grade 11 you did the mesas. What else did you do? The plateau, the conical hill. You still remember? The butte. Okay, so we are saying match this 8. What is the answer there? What is the answer? That is 3.2.5. 8, which shows the cross section. Can you see the way it looks? Is it A, B, C, or D? You can see it's more of a conical hill. It looks like the rock cap has been removed there. If you look at it, it's more of a conical hill. It's more of your B, 3.2.5. If you look at it. Can we say conical or butte? But I'm seeing like if you look at the top, which one is the cross section? If you look at this, which one is the correct cross section? I'm seeing B. B. All right. Then can we proceed? Refer to block A4 in the topographical map. A4 on the topographical map. This is A4 on the topographical map. In which direction is the river G flowing? Here, in which direction is the river G flowing? In which direction is river G flowing? In which direction is river G flowing? Remember what we said? The tributaries, they join at acute angle. Yeah, is west, because you have got these tributaries joining at acute angles, is flowing towards the west. So it's flowing towards the west, westwards. That's correct. What else can you use? Okay, the angle at which it flows. Okay, yeah, I think let's just use west. Okay, that's correct. Then how do tributaries assist in identifying the direction in which the river G flows? Tributaries, they join at acute angles. They are joining at acute angles, less than 90 degrees. That's what is happening. The tributaries are joining at less than 90 degrees. That's how you can explain that. The tributaries are joining at less than 90 degrees or at acute angles. Okay, can we proceed? Give me a thumbs up so that we can proceed. We are now doing 3.3 GIS. GIS 3.3. We are almost done. 3.3 GIS. What do we have? 3.6. Refer to the demarcated area in block A1. Refer to the demarcated area in block A1 on the A1, block A1 on the topographical map. A1, they demarcated this one. Can you see? This is the demarcated H. Demarcated this one. Can you see the demarcated area? All right, let's go back to the question. The non-perennial rivers in the demarcated area are an example of non-perennial in the demarcated area is an example of what? The non-perennial are an example of what? What is the correct answer? 3.3.1. What is the correct answer there? In non-perennial rivers in the demarcated area are an example of here in the demarcated area. This non-perennial river in the demarcated area is an example of what? From given vector. Remember, guys, when we talk about whenever we mention topographic map, is vector data. Topographic vector, line, points, and area symbols. That is your topographical line, point, and area symbol. Topographical line, point, and area symbols. Okay, so that is your vector. Then which GIS concept describes the process of demarcation of A1? Which GIS process, the demarcation that we have here? What do we call this demarcation of this H? What do we call it? That is your buffering. That is your buffering. Are we all fine with that? Let's move on to 3.3.3. It reads, give evidence to show how this process was implemented to demarcate the non-perennial rivers. Give evidence to show. Give evidence. That's 3.1.3. What do we have? There are no buildings in the demarcated area. You can see there are no buildings in the demarcated area. The question is saying, give evidence to show how this process was implemented to demarcate the non-perennial rivers. Number one, we are saying, if you look at this, there are no buildings in the demarcated area. You can see here, there are no buildings in the demarcated areas. No cultivation is visible. No human activity or any development is visible. Okay. A wall or a black line was used to demarcate the area around the rivers. So that is how you answer that question. Is it clear? So that we can move on to the next point. Is this clear? 3.3.3. Yeah, no settlements, no development. That's correct. Let's look at 3.3.4. Identify two examples of data layers that were considered by GIS specialists before developing the land strip in B4. Before they put the land strip in B4, which data layers did they consider? Remember, we said, guys, when it comes to data layering, for them to come up with this map, they have put the different layers on top of each other. We have got a layer that shows the relief, that is your contour lines. We have got a layer that shows the infrastructure. I'm talking about the buildings, the roads. We have a layer that shows the vegetation, a layer that shows the different land uses, where you've got your cultivated land, where you've got your built-up areas. So the question now is saying, identify two examples of data layers that were considered in GIS specialists before developing the land strip in B4. This is the B4. Which data layers did they consider? You can see those cube thing is the buildings. They consider that. They also consider the road. You can see there's a road passing there. They also consider the road. What else? The contour lines as well. They are contour lines that shows the relief. What else? Rivers, which is also part of the drainage. That's what they consider. Those are the different data layers that they considered. So it's the rivers, the roads, rivers part of the drainage layer, roads part of the infrastructure layer, what else? Buildings part of the land use layer, then contour lines part of the topograph or relief layer. Then you can also include rock structure or soil structure, part of the geology layer. Is it clear? Is this clear? 3.3.4, thumbs up if it's clear. Thumbs up if it's clear. So in short, do you understand data layering? Are you fine with data layering? Sharp. Let's move on. The last one. Why is it important for GIS specialists to utilize the layers identified in question 3.3.4? The layers that we have identified, remember, why is it important? Why is it important for the GIS specialists to utilize the layers that identified in 3.3.4? The different layers that we identified, what are the importance of identifying them? You can talk about the rivers that we talk about, the drainage there. You want to determine the level of drainage or water load. What else can you talk about? What else can we talk about? To assess the possibility of flooding, that's part of drainage as well. To determine the possibility of the landing strip. What else of your contours, the topography? What else? To determine the availability of open space. So, boys and girls, I think this takes us to the end of our life, guys. Thank you so much. Thank you so much. Thank you so much, guys, for sticking with me from the start until now. Please, can you go to my YouTube, guys? It's on my link. It's on the link. It's on TikTok bio. Go to my YouTube. Just subscribe, guys. You don't pay. You just click on the subscribe button. Please, that's how you can thank me. That's how you can thank me. Please, just the subscribe button on my YouTube. Please do that. Do that when you have a time. When you have time, just hit the subscribe button. I think I've got more than I'm almost close to 50,000 followers. Please, if you can go to YouTube channel and hit the subscribe button. You are not paying anything. You just hit the subscribe button. Please share with your friends. Share in your groups, subject groups, please, so that I can have as many as possible subscribers on my YouTube channel. Please, can you do that for me? Thank you so much, guys. Thank you so much, guys. Thank you. I think we started at 7. We're finishing off now at 10. I need to rest as well. I'm going to work tomorrow. Before you, can you tap the screen before you go? Tap the screen. Tap the screen before you guys tap the screen. Tap the screen. Thank you so much. Thank you so much. Can you tap the screen before you go? Tap the screen. In 2021, some of you requested the 2021 paper yesterday. You said you want the 2021 paper. It's part of your revision. That's why I had to do it. Please tap the screen before you go. I also want diamonds, guys. Just, okay, you just click, you just tap on the screen, guys, before you go. Thank you so much, guys. Thank you so much. I really appreciate it. Thank you so much. You have a blessed setting. Have a blessed evening. Thank you so much. Bye.